In the vast, silent darkness of space, where stars are born and galaxies collide, lies a place so cold it defies belief, a region where temperatures dip to just 1 degree above absolute zero. This is the Boomerang Nebula, a ghostly cloud of gas and dust drifting 5,000 light-years from Earth, and it holds the title of the coldest known place in the universe. Colder than the cosmic microwave background itself, this bizarre nebula challenges our understanding of physics, temperature, and the violent beauty of dying stars. How can something in the universe be colder than space itself? The answer lies in an extraordinary and mysterious process unfolding at the heart of this cosmic anomaly. But before we continue, subscribe to the channel so you don't miss out on any of these videos. In this video, we are going to take you on an extraordinary journey across the galaxy and deep into the very boundaries of scientific understanding to explore the astonishing reality of the Boomerang Nebula. We will look at how it was discovered, what it tells us about dying stars, the physics behind its bone-chilling cold, the mystery of its shape and formation, and its eerie beauty captured through radio telescopes and submillimeter imaging. We'll even explore how scientists managed to measure its unimaginable temperature, colder than the background temperature of the universe itself, and why this fact alone challenges everything we thought we knew about cosmic thermodynamics. To truly appreciate the Boomerang Nebula, we must first understand what it is, and what it isn't. The Boomerang Nebula is a protoplanetary nebula, a stage in the death cycle of a star that's transitioning from being a red giant to becoming a white dwarf. Not to be confused with a planetary nebula, which is a slightly later phase, the protoplanetary nebula stage is rare and short-lived on cosmic timescales. It represents a period where the dying star ejects vast amounts of gas and dust into space, forming a nebula that glows not from its own light, but from the scattered or reflected light of the central star. What makes the Boomerang Nebula so fascinating is its temperature. At 1 Kelvin, or -272.15 degrees Celsius, it is colder than the cosmic microwave background radiation, which itself measures at 2.725 Kelvin. To grasp the gravity of this, remember, the cosmic microwave background (CMB) is the residual thermal radiation from the Big Bang and is generally regarded as the baseline temperature of the universe. So, for something to be colder than the baseline is almost a violation of the expected order of things. The Boomerang Nebula resides in the constellation Centaurus, around 5,000 light-years from Earth. It was discovered in 1980 by astronomers Keith Taylor and Mike Scarrett using ground-based optical telescopes. They noticed an unusual shape in the sky, one that appeared asymmetrical and curved, like a celestial boomerang thrown across the void. The name stuck, though later observations would challenge the original visual impression. In 1995, astronomers using the Swedish ESO submillimeter telescope in Chile made the stunning discovery. This region was colder than any previously observed place in the universe. How could that be possible? Let's consider the mechanics of temperature in space. Space is not a complete vacuum, but it is incredibly close. And temperature, in physics, is not just a number. It's a measure of the kinetic energy of particles. In other words, the lower the temperature, the less movement the particles have. Absolute zero, 0 Kelvin, is the theoretical point at which all molecular motion stops entirely. Reaching absolute zero is impossible by the third law of thermodynamics, but the Boomerang Nebula comes about as close as nature allows. In the case of the Boomerang Nebula, its record-breaking cold is attributed to the extremely rapid expansion of gas from its central star. That expansion, much like the expansion of air in a refrigerator's compressor, causes a dramatic cooling effect. The star at the heart of the nebula is shedding mass at an unusually high rate, about 100 times faster than typical stars in this phase. It is spewing gas outward at speeds approaching 164 kilometers per second, which creates a massive, rapidly cooling envelope of gas around it. This expanding gas absorbs whatever little heat is present, and then disperses it so effectively that the region becomes colder than the ambient temperature of the surrounding universe. In essence, the Boomerang Nebula is a natural cosmic refrigerator, operating on principles that we barely understand, even now. It's like the universe itself taking a deep breath and then letting it out in one long, cold sigh. Now, Imagine the visuals of such a place. The Hubble Space Telescope captured stunning images of the Boomerang Nebula in visible light. Rather than a true boomerang shape, it resembles a glowing bow tie or hourglass, with symmetrical lobes expanding outward from the central source. This shape is thought to be the result of the gas being ejected through two opposing cones, possibly shaped by the influence of a binary star system or magnetic fields. The center of the nebula is shrouded in thick dust, which blocks visible light and forces astronomers to rely on infrared and submillimeter wavelengths to peer inside. This is where instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, come in. Located high in the Chilean Andes, ALMA can detect the faint thermal radiation emitted by cold gas molecules. It allows scientists to measure temperature distributions across the nebula with incredible accuracy. Using ALMA and similar tools, researchers have constructed a detailed temperature map of the Boomerang Nebula, confirming that large swathes of it truly hover around the 1K mark. But the questions don't stop there. Why is this star shedding so much material so quickly? What triggered this rapid cooling? Is this a unique occurrence, or are there other, colder places out there that we haven't found yet? To begin answering these, astronomers have turned to theoretical models of stellar evolution, particularly the later stages of stars similar in mass to our own Sun. The theory goes something like this. As a star like the Sun nears the end of its life, it runs out of hydrogen in its core. Fusion slows down, and the star begins to swell into a red giant. In the red giant phase, helium and heavier elements begin fusing in shells around the core, creating unstable layers and leading to strong stellar winds. Eventually, the outer layers of the star are ejected into space, forming a nebula, while the core contracts into a white dwarf. The process is violent, chaotic, and riddled with feedback loops that can alter the star's behavior dramatically depending on minute differences in composition, mass, rotation, and binary companions. In the case of the Boomerang Nebula, something about this dying star, possibly a fast-spinning core, or an unseen companion star siphoning material, caused it to eject matter at a pace and volume so extreme that it resulted in the ultra-cold conditions we observe today. And the story doesn't end here. Let us now continue this epic journey into the heart of the Boomerang Nebula, an entity that's not just a curiosity, but a profound riddle etched into the sky, one that has pushed the boundaries of what we thought we knew about the limits of cold, stellar death, and thermodynamic behavior in deep space. To better grasp just how the Boomerang Nebula works, we need to take a microscopic and macroscopic approach, one that dives deep into the molecular mechanisms behind cooling and energy dispersion, and another that zooms out to view this structure as part of the grand ballet of stellar evolution. Let's start with the mechanics. The gas in the Boomerang Nebula, composed primarily of molecules like carbon monoxide, CO, hydrogen, H2, and trace amounts of other compounds, is expanding at a rate that is both consistent and swift. In thermodynamics, when gas expands rapidly without gaining heat from its surroundings, it undergoes what's called adiabatic cooling. Think of it as the opposite of compressing air in a bicycle pump, which heats up due to energy concentration. Here, the gas is stretching out into space so fast that any internal energy it contains becomes diluted across a vast volume. And in a nearly frictionless vacuum, there is little to reheat the gas or slow it down. This is how temperatures drop to extremes, almost asymptotically approaching absolute zero. Now imagine that in 3 dimensions, a huge, invisible balloon expanding around the dying star, so quickly that the particles inside it are being pulled apart faster than they can bounce around. It's like the universe's own cryogenic experiment, occurring on a massive scale and driven by the death throes of a sun-like star. This effect is so strong that it even defeats the omnipresent warmth of the cosmic microwave background radiation, the thermal remnant of the Big Bang that permeates every cubic centimeter of space. The CMB sets what scientists consider the thermal floor of the observable universe, roughly 2.725 K. For any region to cool below that, it would need to shield itself from this universal glow or actively remove more energy than it receives. The Boomerang Nebula doesn't block the CMB in the traditional sense. Instead, the cooling is so rapid and efficient that any absorbed CMB energy is effectively diluted and lost in the expanding mass of gas. That's why, at its coldest points, this nebula reaches temperatures around 1K. Now, why does this matter so much? Why should anyone care about a freakishly cold gas cloud 5,000 light-years away? Because it reveals something essential about how stars die, and more importantly, it showcases that the final moments of a star's life can be surprisingly creative in their destructiveness. For decades, astronomers studied stellar death primarily in the context of massive supernova explosions or quiet planetary nebula formation. But the Boomerang Nebula hinted at a transitional stage of profound complexity, one that is more dynamic and extreme than we ever thought possible. It has opened the door to a new category of dying stars that don't go out with a bang, but instead with a whisper, an icy, ghostly exhale of matter into space. This has implications far beyond just this one nebula. It has forced a reevaluation of stellar models. If one such object could cool this dramatically, then others may be out there, hidden by their dim light and difficult-to-detect temperatures. They may be hiding in the shadows, emitting only the faintest whispers of radio waves, invisible to all but the most sensitive instruments. The Boomerang Nebula may be the first of its kind discovered, but it's likely not the only one. Let's consider another point. How do astronomers actually measure such extreme cold in a nebula thousands of light-years away? The process is more complex than sticking a thermometer into space. Scientists rely on spectroscopy, particularly in the millimeter and submillimeter ranges, to detect the rotational and vibrational modes of molecules like carbon monoxide. These modes are temperature-dependent. By measuring the emission and absorption lines associated with these molecular transitions, astronomers can infer the temperature of the gas with extraordinary accuracy. The Swedish ESO submillimeter telescope and later ALMA were able to detect these faint emissions and model the velocity of the outflowing gas. By combining this data with assumptions about the density and volume of the gas, a temperature profile was constructed. The result was staggering. Not just a cold spot, but a sustained, expansive region of interstellar medium that defied previous expectations. And then there's the visual spectacle of the Boomerang Nebula. While its submillimeter profile paints the picture of an invisible, cold region, Hubble's observations in visible light show us an entirely different structure. What we see in optical wavelengths is a glowing, ethereal hourglass figure, shaped by the biconical outflow of material from the central star. This dual-lobed shape, seen in many protoplanetary nebulae, suggests complex dynamics at the core. It's possible that a binary companion, perhaps a smaller star or even a massive planet, orbits the dying star and plays a role in shaping the expelled material. Alternatively, powerful magnetic fields may be channeling the gas into symmetrical jets. The result is a kind of celestial lighthouse, beaming matter into space in opposite directions, and freezing space around it as it goes. Now pause for a moment and consider the implications of all of this. We are witnessing the death of a star, something that happens over thousands to tens of thousands of years, through the lens of modern technology, and what we find isn't merely destruction. It's beauty, structure, an intelligent orchestration of matter into forms and temperatures that challenge the imagination. The Boomerang Nebula isn't just a place. It's a process, frozen in time. And that time is precious. The stage this nebula is in will only last a blink of an eye on cosmic timescales, perhaps 1,000 to 10,000 years. Eventually, the central star will lose enough mass that the outflow slows, the gas warms, and the object becomes a true planetary nebula, glowing brightly as ultraviolet light from the hot core ionizes the gas. But for now, it remains in this fragile, cold state, a living fossil of a dying star. And that leads to a deeper reflection. The Boomerang Nebula is not just the coldest place we know of, it's also a transient place. It won't be the coldest place forever. In fact, in galactic terms, it's a brief whisper between two great exhalations, before the star becomes a white dwarf, and after it was a red giant. What we are seeing is the thermal signature of a star's soul slipping away. And now we ask, how rare is this? Could such phenomena be more common than we think? How do astronomers go about looking for other ultra-cold nebulae in the galaxy? One method is to analyze data from wide-field sky surveys that pick up faint infrared signatures. Instruments aboard spacecraft like the Herschel Space Observatory have proven useful in identifying similar objects, though none have matched the frigid extremity of the boomerang. But as technology improves, especially in the realm of far-infrared and sub-millimeter detectors, the next coldest nebula may be just a detection away. And this leads us to one of the most provocative questions: could there be places in the universe even colder than the Boomerang Nebula that we simply haven't found yet? Statistically, it's possible. The galaxy contains hundreds of billions of stars, and a fraction of them will die in similar ways. The sheer scale of the universe practically guarantees that more of these cosmic freezers exist. But the Boomerang Nebula stands as our first glimpse into such extremes, a beacon, or rather, an anti-beacon, of coldness in the dark. There's also a philosophical element to this discovery. In human experience, cold is discomfort. Cold is death. But in astrophysics, cold can be a fingerprint. Cold can be structure. Cold can be beautiful. The Boomerang Nebula isn't a frozen wasteland, it's a masterpiece of entropy, shaped by the laws of thermodynamics and stellar evolution. It is art written in the language of atoms, motion, light, and time. But the story of the Boomerang Nebula is not just about what we found. It's about what we don't understand. There are mysteries inside that cold gas, molecular reactions that may only occur at near absolute zero, unknown compounds that may form only in the vacuum of space, and interactions between magnetic fields and plasma jets that defy current models. The Boomerang Nebula, in all its frigid silence, may hold clues to physics we have yet to uncover. Continuing our descent into the enigmatic Boomerang Nebula, we arrive at another layer of mystery, one not just painted in coldness and dust, but in questions about the origin of its extraordinary geometry. The double-lobed hourglass structure, symmetrical yet soft-edged, hints at forces more complex than a simple stellar wind. This brings us to a compelling consideration in astrophysics. How do dying stars form such precise shapes? The hourglass formation isn't unique to the Boomerang Nebula, but it is certainly one of the most dramatic examples. Its wings stretch tens of thousands of astronomical units outward, 1 AU being the distance from the Earth to the Sun. The precision of this shape suggests either a central sculpting force or a symmetry-breaking interaction. A binary star system is one of the most likely culprits. Many stars in our galaxy are not alone. They orbit companions, some visible, some dim and elusive. If the dying star at the heart of the boomerang has a stellar partner, then that companion could be influencing the way the gas is ejected. Here's how this might work. As the main star expands into a red giant and begins to shed its outer layers, the gravitational presence of a nearby star disrupts the uniformity of this mass loss. Material preferentially escapes along the polar axis rather than in a perfect sphere. The rotating binary system may even create spiral patterns in the outflowing gas, a phenomenon observed in other protoplanetary nebulae. In the Boomerang Nebula, this could have led to the sculpting of two massive lobes, fanning outwards in a cosmic breath that chills the surrounding universe. This structural formation is more than aesthetic, it is diagnostic. By studying the shape and distribution of the gas, astronomers can reverse engineer the forces at work. Using Doppler shift measurements and detailed modeling, scientists can determine which parts of the nebula are moving toward us and which are receding. This reveals a three-dimensional dance of matter, giving us a fuller picture of how the star's last moments are orchestrated. But there is a paradox embedded in this process. The Boomerang Nebula is not just symmetrical, it's dynamically symmetrical. That means it is evolving in a way that preserves its shape even as the gas moves outward at astonishing speeds. One hypothesis suggests that the ejected material is being shaped by shock fronts, waves of pressure generated by the fast outflow slamming into slower-moving gas. These shocks can compress and cool the material further, aiding the formation of molecular clouds, and reinforcing the symmetry of the structure over time. And what of the star at the heart of this nebula? We can't see it directly, not yet. It is hidden behind a veil of dust and frozen gas. But we infer its existence from the energy required to propel the surrounding material. Based on estimates of mass loss and expansion velocity, The progenitor is thought to be a low to intermediate mass star, one not unlike our Sun. It has likely burned through its hydrogen fuel, expanded into a red giant, and is now shedding its envelope as it prepares to collapse into a white dwarf. This is significant for a number of reasons. First, it shows us what our own star might experience billions of years from now. As the Sun ages, it too will expel its outer layers, potentially forming a nebula, though perhaps not as cold or extreme as the Boomerang. But more importantly, this process is part of a larger cycle of cosmic recycling. The atoms released into space by dying stars eventually coalesce into new stars, planets, and possibly life. The carbon in your body, the oxygen you breathe, all of it was forged in stars like the one at the center of the Boomerang Nebula. So in a very real sense, we are connected to this icy void. It is not an alien structure in a faraway corner of the galaxy. It is a mirror of processes that make existence itself possible. And its extreme nature offers a unique laboratory for studying the behavior of matter and energy at the edge of known physics. One of the most compelling aspects of the Boomerang Nebula is how it bends our expectations of time. In everyday life, temperature changes rapidly, a hot drink cools in minutes, the air warms with the sunrise. But in astrophysics, cooling is usually a slow, almost imperceptible process. Massive clouds of gas and dust in space can take millions of years to cool, if at all. Yet the Boomerang Nebula cooled dramatically in just a few thousand years, less than a heartbeat in cosmic terms. This acceleration of thermal decay suggests not just an efficient mechanism but a rare one. The conditions that created the Boomerang Nebula may require a confluence of factors so precise that they rarely occur together: a specific mass range of the dying star, the perfect distance and angle of a binary companion, the ideal density of surrounding interstellar medium, and perhaps even a magnetic field geometry that focuses the outflow. And now let us entertain an even deeper mystery. Could there be exotic particles or physics at work inside the Boomerang Nebula that help explain its anomalous coldness? Some scientists have speculated whether unknown processes could be aiding the cooling. For example, if there are interactions involving dark matter or neutrinos in these regions, they might play a role. Though this is speculative, the Boomerang Nebula provides an incentive to search. Any location that exhibits such extreme properties becomes a candidate for testing the limits of our theories. It is possible, though not confirmed, that the cold environment might allow for novel chemistry or particle behavior unseen elsewhere. This is especially tantalizing in the context of prebiotic chemistry, the molecular precursors to life. While the Boomerang Nebula is far too cold and dynamic to harbor life as we know it, the molecules forming within it might be part of the molecular toolkit that eventually seeds more stable regions of space. Complex organics have been found in other cold regions, and it's conceivable that the ultra-low temperatures here could stabilize rare, fragile molecules long enough for them to migrate elsewhere. In that sense, the Boomerang Nebula becomes not just a graveyard of a star, but a crucible of creation, a frozen forge in the darkness, crafting the building blocks of future systems. As we widen our lens, it's important to consider the role of observation itself. What we know about the Boomerang Nebula has come from a synthesis of many instruments: submillimeter radio telescopes, optical imaging from Hubble, and spectroscopic data from observatories around the world. This multilayered approach allows us to see the nebula across the electromagnetic spectrum. Each wavelength reveals a different face. Optical reveals dust and light scattering, submillimeter shows us molecular gas, and infrared cuts through the obscuring dust to hint at the central star's heat signature. In recent years, ALMA, the Atacama Large Millimeter/Submillimeter Array in Chile, has provided perhaps the most detailed observations. With its unparalleled resolution, ALMA has captured the velocity maps of the nebula with extraordinary clarity. We can now trace the flow of molecules like carbon monoxide with precision, mapping the contours of coldness itself. These data sets are being analyzed with advanced algorithms, sometimes involving machine learning, to search for patterns that might escape the human eye. Each pixel of data brings us closer to decoding the nature of this anomaly. And yet, with all this technology, we are still in the early days of understanding. The Boomerang Nebula may hold surprises we haven't even imagined yet. Its interactions with the interstellar medium, its internal magnetic topology, the fate of its central star, all of these remain active areas of research. In the vast silence of space, the Boomerang Nebula speaks in frequencies, in light curves, in velocity profiles. It tells a story of death and dispersal, of structure born from collapse. It is a monument to entropy, and yet, paradoxically, a bastion of order, a symmetric, sculpted form in the midst of cosmic chaos. And so, the deeper we look, the more it becomes clear, the Boomerang Nebula is not just the coldest place in the known universe. It is a frontier, a limit case that tests our knowledge, challenges our instruments, and stretches our imaginations. It is not just a place in space. It is a question. A beautiful, frozen question. As we continue our exploration into the enigmatic Boomerang Nebula, we must address the haunting paradox it presents to science. How something so structurally beautiful, so extraordinarily frigid, can exist in a universe that, by its very nature, tends toward chaos, heat, and expansion. The Boomerang Nebula not only defies conventional astrophysical expectations, it reshapes them. Let's return to its core property, the temperature of just 1 Kelvin. This is -272.15 degrees Celsius, just 1 degree above absolute zero, a temperature where virtually all molecular motion ceases. To place this in perspective, even the cosmic microwave background radiation, the leftover heat from the Big Bang, blankets the universe at about 2.7 Kelvin. That means this nebula is colder than the residual glow of the entire universe. If the universe is the ocean of existence, then the Boomerang Nebula is its coldest trench. But how is such a temperature even possible? It all comes down to expansion, extreme, rapid expansion. When gas expands without exchanging heat with its environment, an adiabatic process, it cools. This is similar to how compressed air escaping it can feel cold to the touch. Now scale that to cosmic proportions. In the Boomerang Nebula, gas is ejected from the central star at over 160 kilometers per second, expanding so rapidly that it undergoes intense adiabatic cooling. The result, a molecular outflow so cold that it dips below the background temperature of space itself. This level of cooling was first detected in the 1990s, when astronomers using ground-based telescopes noticed something odd. The radio emissions from the nebula, particularly from molecules like carbon monoxide, were consistent with temperatures lower than the cosmic background. These findings were confirmed by the Swedish ESO submillimeter telescope, and later, by ALMA, providing one of the most surprising revelations in modern astrophysics. Now imagine the kind of environment such coldness fosters. At these temperatures, quantum mechanical effects begin to dominate. Molecular motion is drastically reduced, allowing scientists to study behaviors that are typically only observable in laboratory cryogenics here on Earth. The nebula becomes a natural freezer, preserving molecules in a sort of suspended animation. This offers an unprecedented opportunity to study astrochemistry in a context no laboratory could ever recreate. At these ultra-cold temperatures, strange molecular species could survive, molecules that would normally be torn apart by heat or radiation. The Boomerang Nebula could contain rare radicals, long carbon chains, and exotic ions, all locked in place by the cryogenic environment. This opens the door to the potential for prebiotic molecules forming in the most unexpected place, a dying star's ejected shell. It's also worth noting how the Boomerang Nebula compares to other protoplanetary nebulae, a rare and brief stage in stellar evolution. This phase occurs after a star has exhausted the helium in its core, just before it collapses into a white dwarf. Most such nebulae are chaotic, turbulent, and often radiate in the infrared or visible spectrum. But the Boomerang's peculiar shape, intense cold, and speed of expansion distinguish it as utterly unique. Why don't we see more nebulae like it? One possible answer is that we simply don't have the tools to detect them. The Boomerang Nebula's features are best observed in the submillimeter range of the electromagnetic spectrum, an area notoriously difficult to observe from Earth due to atmospheric interference. It's only with the advent of high-altitude observatories and arrays like ALMA, sitting at over 5,000 meters above sea level in the Atacama Desert, that we can peer into this hidden coldness. What once appeared as just another cloud of gas has revealed itself as the coldest known object in the universe, thanks to advances in technology and observational strategy. But this raises another intriguing thought. Could there be even colder regions out there that we simply haven't detected yet? If rapid expansion is the secret ingredient, then any dying star undergoing an unusually violent ejection phase might produce similar conditions. But unless the geometry, viewing angle, and observational instruments align perfectly, these cosmic cryostats might remain hidden from view. Let's also examine the lifetime of this phenomenon. The Boomerang Nebula's status as the coldest place in the universe is not permanent. As the ejected gas continues to expand and lose momentum, it will slowly begin to interact with the surrounding interstellar medium, heating up again over tens of thousands of years. Eventually, ultraviolet radiation from the exposed core of the star, the forming white dwarf, will begin to ionize the surrounding gas. This process will transform the Boomerang Nebula from its current protoplanetary phase into a more typical planetary nebula, glowing in visible light with intricate patterns of color and shape. This is a stark reminder that nothing in the universe, not even the coldest known object, is eternal. The Boomerang Nebula is a snapshot of a fleeting moment, a star caught in the act of transformation, wearing a veil of ultracold gas that will one day evaporate into the cosmic void. Yet, while the nebula's physical features will change, its legacy in astronomy is permanent. It challenges our models of stellar evolution, of gas dynamics, of radiative cooling, and of molecular chemistry in extreme environments. It proves that even in the darkness of death, there is room for revelation. We must also consider the philosophical dimension this nebula provokes. In a cosmos born from a blindingly hot Big Bang, it is a profound paradox that something can be so cold. The Boomerang Nebula is not a remnant of the early universe, yet it has managed to plunge below the thermal relics of creation itself. It reminds us that the universe is not just a place of immense energy and expansion, but also of quiet collapse, of stillness, of cold. In our search for understanding, we often chase the bright, the blazing stars, the powerful black holes, the seething plasma of galaxy clusters. But sometimes it is the dimmest, the quietest, the coldest places that teach us the most. The Boomerang Nebula whispers truths that supernovae scream. It is an object of silence, and in that silence, a kind of cosmic poetry. In terms of pure observation, one cannot help but be captivated by the aesthetics of this nebula. The symmetry of its wings, captured in stunning Hubble images, evokes a sense of balance that is almost unnatural. One lobe mirrors the other with such precision that it seems as though some unseen sculptor shaped it by hand. This is the delicate dance of physics, gravity, velocity, magnetic fields, and radiation, working in concert to produce something both alien and eerily familiar. And in those elegant curves lies a story of struggle. A star shedding its skin. A gravitational field wrestling with outward pressure. Atoms once fused in a nuclear inferno, now drifting apart in a frozen fog. The Boomerang Nebula is the death mask of a star, but it is a mask still changing, still unfolding. Imagine, then, what we might learn if we could send a probe there, an interstellar mission equipped with sensitive instruments designed to study ultracold matter in the field. What kinds of particles might it detect? Could we find complex molecular structures preserved in the ice? Could it shed light on the formation of the earliest molecular clouds in our own galaxy's history? This is not idle speculation. Missions like Voyager 1 and 2 have already traveled beyond the heliopause, providing insights into the interstellar medium. The next generation of space exploration might take us even further, perhaps even to the vicinity of distant nebulae like the Boomerang. In a future shaped by interstellar travel, the coldest places in the universe might become the most valuable observatories. And yet, for now, the Boomerang Nebula remains a sentinel at the edge of our perception, a reminder that the universe still holds secrets colder than our minds can easily comprehend. But even as we gaze from afar, the Boomerang Nebula continues to expand, silently, invisibly, relentlessly, carving a deeper cavity of cold in the cosmic fabric. It's difficult to conceptualize just how fast and how large this expansion is. Current estimates place the speed of its ejected gas at over 500,000 kilometers per hour. That's over 300,000 miles per hour, fast enough to travel from Earth to the Moon in under an hour. And yet, this speed isn't driven by explosive violence, like a supernova. Rather, it is the calculated breath of a dying star, a last gasp stretched over centuries, hurling its outer layers into the void in a final, frigid ballet. This velocity matters because it's central to why the nebula has achieved such extraordinary coldness. It's not enough for matter to escape. It must do so rapidly and uniformly for adiabatic cooling to take full effect. Any stalling, any interaction with nearby material, would inject energy and thus heat. The Boomerang Nebula is so pristine in its isolation that the outflow has maintained a nearly perfect, uninterrupted expansion, creating a cryogenic cocoon unmatched anywhere else in the known cosmos. Let's now zoom in, far closer than any telescope allows. At the microscopic level within the expanding shell, something extraordinary is happening. Molecules such as carbon monoxide, CO, silicon monoxide, CO, and perhaps even exotic species like cyanopollenes are moving through the rarefied gas at molecular velocities barely above the quantum ground state. In fact, at 1 Kelvin, the de Broglie wavelengths of these particles become large enough that their quantum behavior becomes visible across macroscopic distances. In the coldest parts of the shell, molecules might begin behaving not just as particles but as quantum waves, potentially forming patterns of interference and coherence that challenge classical chemistry entirely. This opens up fascinating questions for theoretical chemistry and quantum astrophysics. In environments like the Boomerang Nebula, quantum tunneling could play a significant role in reactions. For example, in ultra-cold labs on Earth, certain reactions have been observed to occur not because the molecules had enough energy to climb a chemical activation barrier, but because they tunneled through it. Could similar processes be occurring in the Boomerang Nebula? If so, this might mean entirely new classes of chemical behavior are taking place in that frozen cloud, forming molecular relics that are otherwise impossible to replicate or study in warmer, more chaotic interstellar conditions. There's also the intriguing possibility that the Boomerang Nebula acts as a preservation vault for the chemistry of a dying star. Think of it. The material blown off into space is not just hydrogen or helium. It's a complex mixture of processed elements: carbon, nitrogen, oxygen, perhaps traces of phosphorus and sulfur. These are the building blocks of life, expelled during a red giant's final breaths. Normally, in the vacuum of space, UV radiation and high-energy particles would rapidly ionize and destroy these fragile molecules. But within the cold cradle of the Boomerang Nebula, they may be protected, perhaps even concentrated in forms rarely seen elsewhere. What we are observing, then, is not just a dying star, but a molecular time capsule, a place where atoms forged in stellar furnaces have slowed to a crawl, locked in a freezer at the edge of thermal death. Studying this may allow us to peer into the chemical past of the galaxy itself. Let's step back for a moment and consider the star at the center of all this, the one responsible for the creation of the Boomerang Nebula. This star is no longer on the main sequence. It exhausted its hydrogen billions of years ago, likely fused helium into carbon and oxygen during its red giant phase, and now exists as a post-EGD star, an object in transition. It's incredibly faint invisible light, partly because it's shrouded by the very gases it expelled, but also because much of its emission is in the infrared and radio ranges. One day, it will become a white dwarf, a compact, Earth-sized remnant of its former self. But not yet. At present, it is still transitioning, throwing off the outer layers that form the stunning lobes of the boomerang. The structure of these lobes is also worth diving into. They appear bipolar. That is, they stretch out in two symmetrical directions from the star's poles. This symmetry isn't accidental. It likely results from magnetic fields, stellar rotation, or even the influence of a binary companion star, a hidden partner that may be orbiting the main star and helping shape the outflow of material into a double-lobed jet. These bipolar outflows are not uncommon in protoplanetary nebulae, but in the case of the Boomerang Nebula, the alignment and velocity are unusually extreme. In images captured by the Hubble Space Telescope, you can see a kind of eerie reflection symmetry, a ghostly hourglass shape, hollow and elongated, stretching into the darkness. The lobes are not perfectly spherical but slightly curved, which suggests a precessing jet, perhaps due to gravitational interactions between a close binary pair. Such dynamics could explain the peculiar shape of the gas and even influence the cooling process, by affecting how and where the gas expands. But let's go even further, into the cosmic implications of such a discovery. The Boomerang Nebula forces us to reevaluate what we consider extreme in space. Typically, we associate extremity with heat, black holes, quasars, neutron stars. But here is a place whose defining feature is not energy, but its absence. This flips our intuition. It asks us to consider that coldness, too, can be powerful, that entropy and silence and stillness may hold just as many secrets as violence and flame. And what if the Boomerang Nebula is not alone? What if there are other objects just as cold, or colder, lurking in the vast dark spaces between stars, undetectable by current instruments? As we develop better cryogenic detectors and more sensitive submillimeter arrays, we may discover that the coldest places in the universe are not anomalies, but common stages in the death throes of solar mass stars. Perhaps the Boomerang Nebula is the first of many such objects, a trailblazer in a new category of astrophysical study, cryonebulae. Imagine what such a catalog could teach us. We might learn about the exact thresholds at which molecular clouds fragment. We could gain insight into how molecules freeze, how ices form in deep space, and how this affects the delivery of water and organic compounds to forming planets. In the long term, this could even affect our search for life in the universe. After all, it's not just the heat of stars that shapes habitability, it's also the cold reservoirs that preserve the molecules necessary for life until they can be warmed and used. Thus, in a way, the Boomerang Nebula is not just the coldest place in the universe, it's also one of the most informative. A kind of cosmic observatory, operating at a temperature and scale that no Earth-based lab can hope to match. And then, there's the beauty of it all. Astronomers, physicists, poets, even philosophers, have all looked at the Boomerang Nebula and been moved. Its strange symmetry. Its icy breath. Its lonely place in the cosmos. This is the universe not as fire and fury, but as stillness, as frozen time. The Boomerang Nebula teaches us that not all stars die in loud explosions. Some go gently, casting off their outer layers like veils in the dark, cooling faster than anything we thought possible, whispering their final songs at a temperature where sound itself cannot travel. And so we keep looking. We keep building better telescopes. We keep pushing into the unknown. Because in the quiet cold of space, even dying stars have stories to tell. As we continue our deep exploration into the mysteries of the Boomerang Nebula, we must consider another fascinating dimension, the thermodynamic uniqueness of this place. At 1 Kelvin, just a single degree above absolute zero, we approach a realm where our conventional understanding of physics begins to blur. This temperature is so low that the internal motions of molecules nearly cease, and quantum mechanical effects start to dominate. Unlike the high-energy environments of stars and galaxies, this region offers a rare laboratory in which the absence of heat becomes the defining condition. Let's start by addressing how scientists even know that the Boomerang Nebula is this cold. It's not as if we can simply stick a thermometer into its ghostly cloud. The temperature was determined using millimeter wavelength observations, particularly those that detect the emission and absorption lines of carbon monoxide (CO) molecules. These molecules are crucial because they emit radiation in predictable ways depending on their energy state. When the ATACM, a large millimeter/submillimeter array, ALMA, and other instruments analyzed the Boomerang Nebula, they found that the radiation being emitted was consistent with a temperature of just 1 Kelvin, colder than the cosmic microwave background. Now here's where it gets even stranger. The cosmic microwave background (CMB) radiation, which fills all of space, has a temperature of about 2.725 Kelvin. This radiation is a relic of the Big Bang, and it permeates the entire universe uniformly. That means that everywhere, even in the dark voids between galaxies, you will find this faint afterglow of creation. So how can the Boomerang Nebula be even colder than this seemingly omnipresent background radiation? The answer lies in the adiabatic expansion we mentioned earlier. When gas expands rapidly in space without gaining energy from outside sources, it cools. In most cases, the expansion slows or gets interrupted, and the temperature levels off or rises. But in the Boomerang Nebula, the expansion is so dramatic and sustained, thanks to an incredibly powerful stellar wind, that the gas continues to lose energy rapidly. Essentially, it's expanding faster than the CMB can rewarm it. This allows it to reach a temperature lower than the universal baseline, making it the only known region to defy the thermal floor of the cosmos. This brings us to a deeply philosophical question. What does it mean for something to be the coldest place in the universe? We're not just talking about a curiosity or a record-setting statistic. We're talking about a boundary, an edge, where the laws of physics, thermodynamics, and entropy are pushed to their limits. It's like finding a perfectly calm eye in the middle of the storm of cosmic energy, a place where entropy has seemingly run out of breath. This boundary is particularly important in the context of quantum mechanics, where temperature plays a critical role in determining the behavior of particles. At 1 Kelvin, atoms begin to behave more like waves than particles. Their positions become increasingly uncertain, their velocities governed less by collisions and more by probability. This makes the Boomerang Nebula an astrophysical analog to Bose-Einstein condensates, ultra-cold quantum states produced in laboratory settings on Earth. However, while our best labs can maintain such states for mere seconds and only with isolated atoms, the Boomerang Nebula is doing it on a macroscopic scale, and doing so naturally. There's also the question of dust, not the kind that gathers on your bookshelf, but interstellar dust grains composed of silicates, carbon, and ice. Within the Boomerang Nebula, these grains are incredibly important. At such low temperatures, they act like sponges, absorbing stray molecules and photons, and helping to shield the inner regions from external radiation. Some researchers speculate that amorphous ice, a rare form of water ice found in space, could form here and remain preserved for thousands, if not millions, of years. This ice is different from anything on Earth, structurally chaotic and possibly hosting exotic chemistry within its pores. Could these dust grains be seeds for prebiotic chemistry? That's a big leap, but not a baseless one. Laboratory experiments show that certain molecules necessary for life, formaldehyde, methanol, even amino acids, can form on icy dust grains under the right conditions. If similar processes occur in places like the Boomerang Nebula, it suggests that even the coldest parts of the cosmos may contribute to the chemical foundation of life. While it's unlikely that life itself could arise in such extreme cold, these regions may act as delivery mechanisms for complex molecules to warmer, planet-forming environments. From this perspective, the Boomerang Nebula isn't just a death shroud for a star. It's a chemical factory, a staging ground for cosmic ingredients that could one day find their way into the birth of new stars and new worlds. This makes it part of a grand cosmic cycle, a loop in which stars are born, live, die, and then give back to the universe the materials that made them, allowing the process to begin again. Now let's zoom back out, far, far out. Consider this. There are an estimated 100 billion galaxies in the observable universe. Each of these galaxies contains anywhere from tens of millions to hundreds of billions of stars. Most of these stars will eventually pass through an AGB phase and shed their outer layers, potentially forming planetary or protoplanetary nebulae. That means that objects like the Boomerang Nebula are not rare in principle. There should be millions, maybe billions, of similar events unfolding throughout the cosmos. But only one, so far, has been found to be this cold. Why? This question underscores how difficult it is to detect cold objects in space. We rely heavily on infrared and submillimeter observations, which can only be made with highly sensitive instruments and under the right atmospheric conditions, or better yet, from space-based observatories. Many regions of the sky remain poorly surveyed in these bands. So, the Boomerang Nebula may not be unique in its nature, only in its detectability. That's why missions like JWST, James Webb Space Telescope, and the Future Origin Space Telescope are so important. These telescopes are optimized for the infrared spectrum, precisely the range needed to peer into the coldest, darkest places in the universe. As our observational technology improves, we may begin to uncover a hidden ecosystem of ultracold nebulae, each a window into the dying breaths of stars and the quantum complexity of the interstellar medium. But even if more such objects are found, the Boomerang Nebula will remain iconic. It was the first. The one that forced scientists to recalibrate their understanding of thermal limits in space. The one that reminded us that silence can be more mysterious than sound, and that the end of a star's life can be as elegant as it is strange. In its icy beauty, the Boomerang Nebula offers a mirror to our own fleeting existence. Stars are born, grow, and die. So do planets. So do we. Yet, in death, they leave behind something: material, energy, memory. The Boomerang Nebula is a kind of memory written in cold gas and ancient light. A memory of what the star was. A preview of what it will become. And perhaps, a hint of what lies beyond our own brief, bright moment in the universe. As we continue unraveling the Boomerang Nebula's astonishing nature, it's important to delve into its broader cosmic context, not just as a cold anomaly, but as a vital participant in the galactic life cycle. Every speck of dust, every molecule of gas, and every photon it emits plays a part in shaping the environment of the Milky Way. While the Boomerang Nebula is located approximately 5,000 light-years away in the constellation Centaurus, it still contributes material to the interstellar medium that could influence the evolution of stellar nurseries millions of years from now. Let us imagine what happens to this nebula over astronomical timescales. The gas ejected from the central dying star will continue to expand into space, becoming increasingly diffuse. Eventually, it will lose its distinct shape and blend seamlessly into the galactic dust and gas clouds that drift between stars. These same clouds are the raw ingredients for new stars and planetary systems. So, in an incredibly poetic twist, the coldest object we've ever found is not the final stop in a cosmic journey. It is a beginning for something else. Yet, the process is not entirely passive. As this material joins the galactic tapestry, it interacts with other nebulae, is stirred by supernova shockwaves, or gets compressed by gravitational tides from passing stars. These interactions eventually cause the gas to collapse under gravity, forming dense regions called Bach globules, potential seeds for new star formation. From this perspective, the atoms now in the Boomerang Nebula may one day ignite again in a second generation of stars, carrying forward the legacy of the original star in an eternal loop of destruction and renewal. This is not mere theory, it's observed galactic behavior. We know that most stars are not made from pure hydrogen left over from the Big Bang. They contain traces of carbon, oxygen, nitrogen, silicon, and iron, all forged in the nuclear furnaces of previous stars and scattered by events like this one. When you see the Boomerang Nebula, you are seeing one of these chemical dispersal events in real time, frozen in a phase lasting mere tens of thousands of years. A blink on the galactic timescale, but monumental for our understanding of stellar physics. The Boomerang Nebula also challenges our understanding of morphological evolution in nebulae. While its current shape resembles a bow tie or hourglass, it likely began as a nearly spherical outflow. The shift to its current bipolar structure suggests dynamical forces at play, including the presence of a binary companion or magnetic fields guiding the gas. Magnetic fields, in particular, are still one of the most enigmatic forces in astrophysics. We know they shape everything from solar flares to entire galaxies, yet we cannot directly observe them in most cases. We infer their presence from how matter behaves. In the Boomerang Nebula, the focused outflows and narrow lobes point strongly toward an organized magnetic environment, possibly structured by an inner disk or the gravitational influence of a hidden star. This hypothetical companion, if confirmed, would align with what we know about planetary nebulae in general. A high percentage of them form in binary systems. In these pairings, mass from the dying AGB star can transfer onto the companion, forming an accretion disk. This process can launch collimated jets, which in turn shape the surrounding envelope into the bipolar lobes we observe. These jets can travel at incredible speeds, hundreds of kilometers per second, and produce shockwaves that sculpt the nebula into ever more intricate forms. In the Boomerang Nebula, these interactions are likely what allow for adiabatic expansion to remain so efficient, creating that almost impossible 1 Kelvin environment. Let's now entertain a deeper cosmic mystery. What if there are colder places yet to be found? Could there be regions in the cosmic web, the vast, filamentary structure of dark matter in galaxies, where gravitational voids allow gas to expand and cool beyond what we've seen in the Boomerang Nebula? Theoretically, yes. In underdense regions of the universe, sometimes called supervoids, gravitational acceleration is minimal. Gas in these areas could conceivably expand without heating, leading to local conditions colder than the cosmic background. The problem is detection. With little radiation to observe and sparse matter to emit it, such regions could remain completely invisible to our telescopes for centuries. This brings us to a key insight. The Boomerang Nebula is not just an object. It is a natural thermometer, a benchmark against which all future cold phenomena will be measured. Just as the pulsar PSRB 1919+21 became a cornerstone in understanding neutron stars, the Boomerang Nebula has become a keystone in the study of cold astrophysics. Whether we're developing new cryogenic technologies for space telescopes or studying early universe conditions in lab-based cosmology, we look to this nebula as a point of reference. It informs our models of gas dynamics, molecular behavior at low temperatures, and the very limits of entropy. And yet, despite all this scientific importance, the Boomerang Nebula remains hauntingly beautiful. It's easy to forget, when discussing temperature gradients and spectral lines, that this object is visually stunning. High-resolution images show delicate wisps of gas extending like frozen breath from the dying star at its core. The symmetry is striking, two opposing lobes radiating outward with a narrow waist between them, giving it that iconic boomerang or hourglass shape. The light we see today began its journey 5,000 years ago, when human civilizations were building stone monuments and charting the heavens with the naked eye. It's humbling to realize that something so distant, so cold, and so silent has still found a way to speak to us across eons of time. In that light, the Boomerang Nebula becomes more than a scientific puzzle. It is a cosmic monument, a frozen echo of stellar life, a breath held in the coldest silence of space. As our journey continues, we will delve even deeper into its molecular composition, the role of carbon monoxide and dust in its thermal profile, and what its future may hold as the universe itself continues to cool over the next billions of years. Now, as we descend even further into the intricate layers of the Boomerang Nebula's complexity, we must shift our focus to the molecular chemistry happening inside this uniquely frigid environment. At a temperature of just 1 Kelvin, merely 1 degree above absolute zero, the kinetic energy of particles is almost entirely gone. Under such extreme conditions, chemical interactions behave in ways that are vastly different from those found in warmer regions of space. The Boomerang Nebula, therefore, offers a natural laboratory for studying molecular behavior at the lowest energy states known to the universe. One of the most critical molecules involved in this frigid ballet is carbon monoxide, CO. This simple yet significant compound plays a crucial role in the nebula's cooling process. Carbon monoxide is an efficient radiator of energy through rotational transitions in the radio and submillimeter wavelengths. These emissions allow energy to escape rapidly from the gas, contributing to the profound cooling effect. When the gas expands and emits energy via CO transitions, it sheds heat more efficiently than it would in a vacuum, leading to temperatures that fall even below the background radiation of the universe itself. It's astonishing to realize that the presence of molecules enables the nebula to become colder than the universe's own thermal baseline. The CO molecules, however, do not act alone. The nebula contains traces of other compounds, such as H2, molecular hydrogen, HCN, hydrogen cyanide, and dust grains made primarily of carbonaceous or silicate materials. These elements interact with the light from the central star in complex ways. Some absorb and re-radiate infrared energy, while others shield internal regions of the nebula from external radiation, allowing inner pockets of gas to maintain their frigid isolation. These dust grains also provide surfaces on which chemical reactions can occur, even in low temperatures. Reactions that would be improbable in gas phase chemistry can take place on these solid surfaces, helping to explain the molecular diversity seen even in the coldest parts of the nebula. Interestingly, the cold temperature of the Boomerang Nebula also preserves molecules that might be easily broken down in warmer environments. For instance, ultraviolet radiation from the central star is weak, and even the sparse interstellar radiation field has little effect. This allows fragile molecules, sometimes called complex organic molecules, COMs, to survive and even accumulate. In other nebulae, such molecules might be split apart by UV photons or thermal agitation, but here in the Boomerang Nebula, they endure in near-frozen stasis. This preservation of complex chemistry could provide clues to astrobiological questions, especially regarding how organic molecules form and are protected in space before arriving on planets or comets. Now imagine the implications for astrochemistry. If a future mission could one day send a probe or remote sensing telescope capable of directly studying these molecules in situ, we might uncover the fundamental building blocks of life suspended in one of the coldest cosmic freezers ever known. These findings could revolutionize our understanding of prebiotic chemistry and how life's ingredients might be scattered across the galaxy, not in boiling lava worlds or steamy vents, but in places so cold they make Antarctica look like the tropics. To understand why all this matters, we need to go back to a central truth of physics: temperature dictates behavior. In hot environments, reactions happen quickly, particles move energetically, and structures are unstable. In cold environments, reactions slow, particles settle, and unusual structures, sometimes impossible ones, can form. In ultra-cold environments like the Boomerang Nebula, quantum mechanical effects begin to dominate. Atoms and molecules may begin to exhibit behaviors akin to Bose-Einstein condensation, a state where particles act in collective quantum harmony, blurring the lines between matter and wave. While the Boomerang Nebula is not quite cold enough to generate a true Bose-Einstein condensate, its extreme cold invites the possibility of quantum-scale coherence in molecular clouds, an idea still largely theoretical but tantalizing in its implications. Even more provocatively, this frigid temperature raises fascinating questions about the limits of entropy and time. At such low thermal energy, systems become so ordered that the usual flow of time, driven by increasing entropy, seems to stall. Of course, time continues marching on, but the rate of change within the system slows to a crawl. This has philosophical implications. In the Boomerang Nebula, time appears to stretch, slow, and almost freeze, reminding us that the flow of time is not universal, but relative to energy, motion, and disorder. And let's not forget that the shape of the nebula is as central to its identity as its temperature. The hourglass or boomerang shape is believed to be the result of anisotropic mass ejection, potentially driven by a binary star system. High-resolution images and modeling suggest that gas is not being expelled equally in all directions. Instead, it flows along two polar axes while being restricted in the equatorial plane, likely due to the presence of a circumstellar disk or torus, a flattened ring of material orbiting the star. This asymmetric outflow can be simulated with hydrodynamic models, which often rely on binary interaction as the driving force. Imagine the dynamics at play. A massive, bloated red giant nearing the end of its life begins to lose mass. Some of this material is gravitationally drawn toward a companion star, creating a spiral flow or accretion stream. Angular momentum forces the material into a disk, which in turn channels subsequent gas ejections into narrow jets along the polar directions. These high-speed outflows carve out tunnels in the surrounding envelope, resulting in the iconic bipolar morphology we now observe. The lobes themselves are not uniform. They contain internal shockwaves, knots, and filaments, indications of episodic ejection events, each more violent than the last. And yet, despite its name, there is no boomerang flying through space. The term was coined because of how early images revealed an unexpected reflection of light and shape symmetry. This misnomer only adds to the nebula's mystique, a cosmic object misnamed and misunderstood, until the cold, hard data from ALMA redefined everything. That redefinition is still happening today, as astronomers pore over data sets trying to answer lingering questions. What is the precise age of the nebula? How long will it remain the coldest object? What happens to its central star? Could there be other such objects lurking in our galaxy, waiting to be discovered by next-generation telescopes. Indeed, the future of astronomical observation may hold answers. Telescopes like the James Webb Space Telescope, JWST, which is optimized for infrared and sub-millimeter observations, could yield even more detailed data about the nebula's composition, temperature gradients, and potential central companions. The Atacama Large Millimeter/Sub-Millimeter Array, ALMA, will continue to play a central role, especially with future upgrades enhancing its resolution and sensitivity. And as computational modeling improves, our ability to simulate such phenomena in 3 dimensions will allow virtual recreations that may even help explain why the Boomerang Nebula is so uniquely cold compared to all other known nebulae. The ultimate fate of the Boomerang Nebula, however, remains the same as all planetary nebulae. As the central star continues to evolve, it will shed its outer layers completely, exposing a hot white dwarf core. The surrounding gas will eventually disperse into the interstellar medium, and the striking hourglass shape will blur and fade. But the molecules, the dust, the atoms themselves, these will survive, traveling across the galaxy, perhaps seeding new stars, perhaps falling into the gravity well of a newborn solar system. Some tiny fraction may one day become part of a planet, or even a living being, completing a journey that began in the silent, frozen breath of the coldest place we have ever known. And so, we find ourselves diving even deeper into the unraveling narrative of the Boomerang Nebula, an extraordinary cosmic creation where physics seems to stand still, where light bends and reflects through near-frozen gas, and where mystery compounds mystery. As we continue our exploration, let's now examine how the Boomerang Nebula fits into the larger tapestry of stellar evolution, comparing and contrasting it with other celestial structures that emerge from dying stars. The Boomerang Nebula is classified as a preplanetary nebula, a brief transitional phase in a star's life when it has exited the red giant stage, but has not yet become a full planetary nebula. During this phase, mass loss occurs at dramatic rates, and stellar winds, often asymmetric, create complex structures in the surrounding gas. This stage is one of the shortest lived in stellar evolution, lasting only a few thousand years. Despite its brevity, this stage is pivotal in shaping the final morphology of the star's remains. Most stars that enter the planetary nebula phase do so in a more typical fashion. They shed their outer layers and roughly spherical shells, eventually revealing the hot core that ionizes the gas and causes it to glow in colorful patterns. In contrast, the Boomerang Nebula is not glowing in visible light, not yet. It remains dark and nearly invisible in the optical range because its central star hasn't heated up enough to produce significant ultraviolet radiation. This is precisely why infrared and radio astronomy have become essential in unlocking its secrets. Only at these wavelengths can we peer into the cold darkness and see the whispering motions of gas and dust, the shivers of dying starlight held in stasis. Comparatively, other preplanetary nebulae, like the Egg Nebula or the Red Rectangle, also display dramatic bipolar outflows and dusty envelopes, but none have exhibited the Boomerang Nebula's unique capacity for extreme adiabatic cooling. This raises a profound astrophysical question: why here? Why this nebula, among all the known planetary and preplanetary nebulae, has managed to cool itself below the cosmic microwave background (CMB) temperature? To understand this better, let's consider the cosmic microwave background radiation, the remnant heat from the Big Bang, which permeates the universe at an almost uniform temperature of about 2.73 Kelvin. This is often considered the lowest natural temperature in the cosmos. Yet, the Boomerang Nebula's central region dips as low as 1 Kelvin. How can this be? The answer lies in the powerful principle of adiabatic expansion, a process where gas expands so quickly and dramatically that it loses thermal energy without exchanging heat with its surroundings. It's similar to how compressed air escaping from a can feels cold. The sudden expansion lowers its temperature. Now imagine this occurring on an astronomical scale, with stellar winds moving at over 160 km per second, expanding outward into a low-pressure environment. The gases in the Boomerang Nebula expand rapidly into the surrounding void, causing their temperature to plummet faster than they can absorb any energy from ambient sources like the CMB. It is an elegant dance of thermodynamics in motion, one that results in temperatures lower than any other naturally occurring region in the known universe. This anomaly isn't just interesting, it challenges the boundaries of what we know about energy exchange in space. In theory, no part of the universe should naturally be colder than the CMB unless it is shielded or rapidly expanded, as in this case. This places the Boomerang Nebula in a category of its own, standing as a thermodynamic outlier, almost like a cheat code in the universal rulebook. What's even more fascinating is that this low temperature is transient. Over time, as expansion slows and the star evolves, the nebula will warm up again. Its record-holding coldness is a fleeting phenomenon, a moment in stellar death's longer story. We must now revisit the geometry and kinematics of the nebula, which offer further clues into its formation. Observations made using ALMA and other submillimeter telescopes reveal a highly collimated outflow structure, meaning the gas isn't dispersing in a uniform sphere but rather being pushed through narrow channels or jets. These jets are likely shaped by the gravitational influence of a binary companion, or perhaps even a planetary system. Such interactions create complex gravitational zones that channel mass loss into preferred directions, resulting in the hourglass-like morphology we observe today. Over time, these outflows interact with earlier ejected materials, causing shock fronts and bow shocks, regions where fast gas slams into slower material, compressing it and potentially triggering even more radiative cooling. It's a feedback loop of thermodynamic extremes, where gas that was once part of a stable star is now racing through space, colder than the background of time itself. Furthermore, these outflows can also be responsible for structural asymmetry, which is frequently observed in evolved stars. Astronomers are still debating whether all stars end their lives this way, with bipolar outflows and asymmetry, or whether this is a special case, perhaps induced by the presence of a massive companion, rapid stellar rotation, or magnetic fields. In any case, the Boomerang Nebula becomes more than a cold cloud, it becomes a cosmic autopsy report, offering a freeze frame of a star caught mid-death. Another extraordinary aspect of the Boomerang Nebula is its opacity at certain wavelengths. While it's invisible in most visible light images, it glows in the submillimeter range due to the radiation emitted by molecules like CO. These observations provide critical data on velocity profiles, temperature maps, and density distributions, all of which help astronomers reconstruct the history of the nebula's formation. The CO molecules not only act as thermometers, indicating extreme cold, but also serve as tracers, helping astronomers follow the flow of gas with precision. Moreover, examining the Boomerang Nebula allows scientists to improve their models of stellar mass loss mechanics, especially in low to intermediate mass stars. The importance of understanding these processes cannot be overstated. Stars like our Sun will one day enter this evolutionary path. By studying the Boomerang Nebula, we are, in a sense, peering into our own distant future. The Sun will eventually swell into a red giant, shed its outer layers, and perhaps, if the conditions align, form a preplanetary nebula. It may not reach the frigid lows of the Boomerang, but the underlying physics will be the same: mass loss, expansion, cooling, and transformation. The central star of the Boomerang Nebula is believed to be low in mass but high in evolutionary age. It has ejected a large portion of its envelope, leaving behind a hot core that has not yet reached temperatures high enough to ionize the surrounding material fully. This transition, from cool to ionizing, marks the turning point into a true planetary nebula, a phase that will light up the Boomerang in brilliant colors visible in optical wavelengths. Until then, it remains a cold, silent whisper in the blackness of space, a celestial secret only revealed through millimeter-wave whispers. As we continue unfolding its mysteries, we must also acknowledge the sheer beauty of the object. In composite images, its symmetrical lobes stretch out like arms, the center dark and opaque, surrounded by faint halos of scattered light. The interplay between symmetry and chaos, order and unpredictability, is what makes this nebula so hauntingly fascinating. It is as if the universe chose to wrap one of its dying stars in the most beautiful shroud imaginable, one that not only dazzles the senses but puzzles the intellect. In the next segments, we will dive even further into the cosmological significance of such cold regions, the ongoing and future research missions targeting the Boomerang Nebula, and how this object may shape our understanding of the thermodynamic limits of the cosmos. The Boomerang Nebula, in its eerily silent stillness and bone-chilling cold, offers more than just a record-breaking temperature. It acts as a cosmic laboratory, an observational gateway into the mechanisms of stellar death, mass ejection, binary interactions, and the very thermodynamic thresholds of the universe. As we go even deeper, let us now shift our focus to the broader cosmological implications of such an object, and why it captivates not only astronomers, but theoretical physicists as well. To fully appreciate the rarity of the Boomerang Nebula's ultra-cold state, it's essential to understand the baseline temperature of the universe. The cosmic microwave background (CMB) serves as a kind of universal minimum. It blankets the cosmos with a nearly uniform temperature of 2.73 Kelvin, left over from the Big Bang, essentially the faint glow of creation itself. In nearly every corner of the universe, even in the darkest reaches between galaxies, it is this CMB that sets the lowest observable temperature. Any temperature lower than this must involve some exceptional process. And yet, the Boomerang Nebula, nestled in our own galaxy, just 5,000 light-years away in the constellation Centaurus, defies this expectation. The central outflows of this nebula dip to 1 Kelvin, and possibly even lower in some estimates. This makes it not only the coldest known natural location in the universe, but one of the few that requires dynamic cooling to reach such a state. This opens up a vital discussion: how does the universe allow such exceptions to exist? The answer is subtle and reveals deep truths about non-equilibrium thermodynamics. In most of space, temperatures are set by thermal equilibrium. Objects absorb and emit radiation until they balance with their surroundings. But in dynamic, fast-changing environments, like in explosive stellar outflows, thermodynamic systems don't have time to equilibrate. Energy is transformed faster than it can be redistributed. This phenomenon is what allows the Boomerang Nebula to momentarily plunge below the CMB temperature. It's not breaking the laws of physics, it's navigating them with perfect timing. Moreover, this dynamic cooling isn't happening by chance. It's tightly related to the rate of mass ejection and the velocity of the outflows, which in the case of the Boomerang are among the most extreme ever recorded in a dying star. Mass is being expelled from the central star at a rate of approximately 10 to the power of -5 solar masses per year, and this material is flying outwards at over 160 kilometers per second. This rate of expansion leads to dramatic adiabatic cooling. The gas loses energy as it expands and spreads into the low-pressure environment of interstellar space. As no additional heat is being introduced to this system, and the environment around it is essentially empty space, the temperature continues to drop. This poses an interesting side question: is it possible that even colder places could exist, just waiting to be discovered? Theoretically, yes, under the right conditions of adiabatic expansion, shielding from the CMB, and the presence of rapidly moving stellar ejecta, a colder natural region could exist. However, such conditions are astronomically rare. So far, the Boomerang Nebula remains the only known natural object to beat the CMB at its own game. But beyond thermodynamics, what other insights does the Boomerang Nebula offer us? It compels us to reconsider the role of asymmetry in stellar evolution. Stars are generally portrayed as perfect spheres, radiating energy uniformly in all directions. However, as we now know, most stars end their lives with complex asymmetrical structures, bipolar lobes, disks, spirals, and jets. These irregularities are not just decorative, they are the fingerprints of binary interactions, magnetic fields, and rotational forces acting on massive scales. In the Boomerang Nebula, we see a highly collimated outflow, suggestive of either a binary companion that is channeling mass loss into specific directions or possibly the influence of a massive planet or toroidal magnetic field. This alone opens up a new chapter in the study of stellar death. The idea that companions, whether stellar or planetary, can dramatically alter the final appearance and behavior of a star. This is not a trivial matter. Roughly half of all Sun-like stars are believed to have companions. This implies that symmetric planetary nebulae might actually be the exception, not the rule. The Boomerang Nebula's dramatic shape and behavior may, in fact, represent a more common end-of-life scenario than once thought. If so, then we may need to rethink our models of stellar evolution to account more explicitly for multi-body dynamics and environmental interactions. On top of this, the Boomerang Nebula helps us refine our understanding of dust formation and molecular chemistry in cold space environments. The gases expelled from the central star contain carbon monoxide, CO, molecular hydrogen, H2, and dust grains, all of which are sensitive to temperature and pressure conditions. In the ultra-cold interior of the nebula, new kinds of ice-coated grains can form, possibly leading to complex organic molecules over time. This kind of cold chemistry may offer analogues to prebiotic chemical evolution, the very chemistry that set the stage for life. Astronomers and astrochemists alike are deeply interested in how complex molecules assemble in space, and the Boomerang Nebula, being colder than any known region, presents a perfect lab for this investigation. Here, reactions that would normally be suppressed or reversed due to heat can proceed in unique ways. It's not a stretch to say that the Boomerang Nebula may hold clues to the kinds of chemical reactions that could happen in the interstellar medium, or even in the protostellar environments that precede planet formation. As we ponder this, we must also marvel at the observational techniques that allow us to glimpse such distant, cold, and dim phenomena. Without infrared and submillimeter telescopes like ALMA, the Boomerang Nebula might still be invisible to us. The use of Doppler shifts to map out the velocity of the gas, combined with spectral line analysis of molecular transitions, enables astronomers to see what the human eye cannot. It's a reminder of how much of the universe remains hidden in wavelengths outside the visible spectrum. And what of the future? Eventually, the central star of the Boomerang Nebula will heat up as it continues shedding mass, eventually revealing its hot core. When it does, it will begin to ionize the surrounding gas, and the nebula will transition into a true planetary nebula. At that point, the cooling will cease, and the temperature of the outflows will rise again, possibly glowing in the blues, reds, and greens so iconic of nebular imagery. This means that the Boomerang Nebula's current status as the coldest place in the universe is temporary. It is a brief, frozen breath in the long exhale of a dying star. In perhaps a few thousand years, a blink of cosmic time, it will heat up and lose its record-breaking title. Thus, what we are witnessing is a fleeting cosmic event, and one that may never be repeated in quite the same way again. And yet, that is part of what makes it so valuable. Its temporality adds urgency to the study, and understanding that the cosmic window is open now, but not forever. Astronomers continue to monitor the Boomerang Nebula, searching for minute changes in temperature, structure, and velocity that might hint at the next stage of its transformation. Every data point adds to our growing tapestry of understanding about how stars live, die, and cool. This brings us to a contemplation. What does the Boomerang Nebula teach us about extremes? We often look to black holes for the most powerful gravitational pulls, to quasars for the brightest beacons, and to supernovae for the most violent ends. But here, in a quiet and invisible patch of the sky, lies a different kind of extreme, an extreme of absence, of stillness, of cold. It is a place so quiet and so cold that it hushes even the whisper of the universe's oldest light. And in that silence, it speaks volumes. To truly grasp the full scope of what the Boomerang Nebula reveals, we must extend our exploration beyond the physics and chemistry, and delve into the philosophical and existential reflections inspired by such a profound natural marvel. This is a place where matter and energy behave in ways that challenge our everyday intuition. Here, the familiar warmth of the sun, the comforting glow of a fire, or even the cold chill of a winter's night pale in comparison to the chilling reality of 1 degree above absolute zero. This cosmic chill forces us to confront the vastness of space as not only an expanse of stars and galaxies, but also a domain of profound extremes. The coldness of the Boomerang Nebula brings us face to face with the concept of absolute zero, the theoretical temperature at which atoms come to a complete standstill, devoid of kinetic energy. Absolute zero is 0 Kelvin, or minus 273.15 degrees Celsius. Scientists have yet to achieve this temperature in the laboratory because quantum mechanics imposes a fundamental limit, but the Boomerang Nebula approaches it naturally through the extraordinary conditions of stellar ejection and adiabatic cooling. It provides a natural laboratory for understanding the quantum behavior of gases at ultra-low temperatures. This quantum realm is not merely an abstract concept but one that shapes how matter behaves at the most fundamental level. At temperatures nearing absolute zero, matter can enter exotic states such as Bose-Einstein condensates, where particles act collectively as a single quantum entity. Although the Boomerang Nebula's gas is not cold or dense enough to form such condensates, its extreme cold hints at the thresholds where such quantum phenomena become dominant. This intersection of astrophysics and quantum mechanics enriches our understanding of the universe's complexity. The nebula's temperature and its ethereal shape also remind us of the life cycles of stars, cycles that span billions of years yet culminate in breathtakingly short and violent events. The Boomerang Nebula represents a fleeting phase lasting mere thousands of years, a blink of an eye against cosmic timescales. Its discovery underscores how our vantage point is always limited by time and space. What we see today might vanish or evolve drastically tomorrow. This transient nature forces us to consider the temporal dimension of astrophysical phenomena, how many extraordinary processes occur unseen simply because we lack the patience or technology to observe them in the right moment. Furthermore, the Boomerang Nebula's extreme cold juxtaposes the more familiar, blazing hot environments in space, such as the blazing cores of stars or the intense energy released by supernovae. It broadens our cosmic perspective, illustrating that space is not uniformly hostile or empty but rather a tapestry of environments with temperatures and energies spanning many orders of magnitude. This diversity is crucial to the chemical evolution of the universe, as different conditions favor the formation of different molecules and dust grains, eventually influencing the formation of planets and even life. Delving deeper into the nebula's molecular composition reveals that the ultra-cold conditions preserve fragile molecules that would otherwise be destroyed in hotter regions. This molecular survival is vital because these compounds, such as carbon monoxide and molecular hydrogen, serve as building blocks for more complex organic chemistry. Observations of the Boomerang Nebula thus contribute to the broader quest to understand the origins of chemical complexity in space, a puzzle that connects directly to astrobiology and the search for life beyond Earth. Additionally, the Boomerang Nebula's discovery was made possible through advances in technology, especially the use of telescopes capable of detecting submillimeter and millimeter wavelengths. These wavelengths are essential for studying cold molecular gas and dust. Instruments such as the Atacama Large Millimeter/Submillimeter Array, ALMA, and the Hubble Space Telescope provided crucial data, revealing the nebula's shape, velocity, and temperature profile. These observations exemplify how technology drives scientific discovery, opening windows to previously invisible phenomena. The Boomerang Nebula also prompts intriguing questions about the role of binary systems in shaping stellar death. Evidence suggests that many asymmetrical planetary nebulae form due to interactions with companion stars or massive planets, which can warp the mass-loss processes and create jets or bipolar lobes. While the central star of the Boomerang Nebula has yet to be conclusively identified as a binary, its complex shape strongly hints at such a scenario. This adds to a growing body of evidence suggesting that stellar companionship dramatically influences stellar evolution and the final morphology of planetary nebulae. Moreover, studying such cold environments helps refine our models of dust grain formation and survival. Dust grains play a pivotal role in astrophysics by facilitating molecule formation, regulating gas temperatures, and acting as seeds for planet formation. In the Boomerang Nebula, the extreme cold conditions allow certain grains to survive or even form ice mantles, providing insight into dust evolution in late stellar phases. Understanding these processes helps piece together the life cycle of dust in the galaxy, which ultimately contributes to the creation of new stars and planets. On a broader scale, the Boomerang Nebula exemplifies the profound interconnectedness of cosmic processes. The death throes of a single star ripple through space and time, enriching the interstellar medium with elements and molecules, influencing star formation, and shaping the chemical milieu from which future solar systems arise. This cosmic recycling underlines the notion that the universe is a dynamic, ever-changing entity, where destruction and creation are inseparably linked. From a human perspective, the Boomerang Nebula challenges our understanding of our place in the universe. It confronts us with the harsh realities of cosmic evolution, but also with the beauty and complexity that arises even in the most extreme conditions. It invites wonder at how much remains undiscovered and how much more there is to learn about the fundamental forces shaping the cosmos. The Boomerang Nebula, with its breathtaking coldness, stands as a testament to the extraordinary diversity of phenomena that exist beyond our everyday experience. It teaches us humility and curiosity, reminding us that the universe is not only a vast expanse of light and heat but also of cold, darkness, and silence, each of which holds keys to understanding the grand tapestry of existence. Exploring further, the Boomerang Nebula's extreme temperature of just about 1 Kelvin, only a single degree above absolute zero, means that it holds a record in the known universe as the coldest natural place discovered so far. This temperature is so low that it rivals the background temperature of the universe itself, which is approximately 2.7 Kelvin. The fact that this nebula is even colder than the cosmic microwave background radiation, the afterglow of the Big Bang, raises fascinating questions about the physical processes that enable such extraordinary cooling. The key to this ultra-low temperature lies in a process known as adiabatic expansion. As the nebula's gas is ejected at incredibly high speeds, around 164 kilometers per second, it expands rapidly into the vacuum of space. This expansion causes the gas to cool down drastically because the particles lose energy as they spread out. Essentially, the gas in the Boomerang Nebula acts like a cosmic refrigerator, cooling itself to temperatures colder than anything we can reproduce on Earth. This phenomenon illustrates the profound power of thermodynamic principles on a cosmic scale, extending classical physics into the domain of astrophysics. Understanding the nebula's formation and evolution requires an appreciation of the life cycle of intermediate mass stars, stars with masses roughly 1 to 8 times that of our Sun. Such stars spend the majority of their lives fusing hydrogen into helium in their cores. Once the hydrogen fuel is exhausted, the star evolves through stages of helium burning and heavier element fusion, eventually reaching a phase known as the asymptotic giant branch, AGB. During this phase, the star becomes unstable and begins to lose its outer layers in a series of pulsations and intense stellar winds. The Boomerang Nebula represents a particularly dramatic example of this mass loss phase, where the star is shedding its envelope at a very high rate. The expelled gas and dust form a circumstellar envelope that interacts with radiation pressure and magnetic fields, creating the nebula's distinctive shape. The rapid outflow and sudden cooling freeze the gas into a cold, expanding shell that glows faintly in millimeter and infrared wavelengths. This glowing shell is what we observe as the Boomerang Nebula. Its distinctive hourglass or boomerang shape suggests complex shaping forces at work. Many planetary nebulae exhibit bipolar or multipolar morphologies, which are thought to arise from mechanisms like stellar rotation, magnetic fields, and interactions with companion stars or planets. In the Boomerang Nebula, the symmetrical lobes suggest a collimated outflow or jet that sculpts the gas as it escapes from the dying star. This provides critical clues about the physics driving asymmetries in stellar mass loss. Moreover, the Boomerang Nebula challenges astronomers to consider the chemical and physical conditions under which molecules survive in harsh space environments. At such low temperatures, molecular hydrogen, H2, and carbon monoxide, CO, remain stable and abundant. These molecules are crucial as they emit radiation at characteristic wavelengths, allowing astronomers to trace the gas's velocity and temperature. Observations have detected strong CO emission lines, which have helped determine the velocity of the outflow and the extent of cooling. The presence of molecular gas at ultra-low temperatures also implies the nebula may harbor dust grains coated with ices, such as water, ammonia, and methane, frozen onto their surfaces. These icy mantles influence the chemistry and opacity of the nebula, affecting how it absorbs and emits radiation. Studying such icy dust grains offers insights into the early stages of molecular cloud evolution and the eventual formation of planetary systems. Technological advancements in radio and submillimeter astronomy have been pivotal in revealing the nebula's secrets. Ground-based observatories like the Atacama Large Millimeter/Submillimeter Array, ALMA, and space telescopes like the Herschel Space Observatory have provided unprecedented spatial resolution and sensitivity, allowing detailed mapping of the Boomerang Nebula's structure. These observations have enabled the creation of velocity maps, temperature profiles, and morphological models, confirming theories about its extreme cooling and shaping. The Boomerang Nebula also serves as a natural laboratory for testing theories of gas dynamics and thermodynamics in space. Its fast-expanding gas shell is an excellent example of supersonic flow in an astrophysical context. The shocks and interactions between different layers of gas produce complex physical phenomena, such as turbulence, instabilities, and magnetic reconnection. These processes are fundamental to understanding how mass and energy are transported in space and have analogues in other astrophysical environments, from supernova remnants to active galactic nuclei. From a broader cosmic perspective, the Boomerang Nebula exemplifies how dying stars contribute to the chemical enrichment of the interstellar medium. As stars like our Sun end their lives, they return processed material to space, including carbon, nitrogen, oxygen, and heavier elements formed during nucleosynthesis. This recycled material becomes the raw ingredients for new stars, planets, and potentially life. By studying objects like the Boomerang Nebula, astronomers trace the flow of matter in the galaxy and understand the origins of the elements that make up everything around us. The cold temperature of the nebula also pushes the limits of our understanding of molecular astrophysics. At temperatures near absolute zero, quantum effects begin to dominate, influencing how molecules vibrate, rotate, and interact. This quantum regime affects the spectra emitted by molecules, making detailed observations essential for refining molecular models and interpreting the signatures we detect across the cosmos. In contemplating the Boomerang Nebula, we also touch on the philosophical notion of cosmic impermanence. The nebula's current state is fleeting on astronomical timescales. Within a few thousand years, it will evolve further as the central star heats up and ionizes the surrounding gas, transforming the nebula's appearance dramatically. This fleeting nature reminds us that the universe is a dynamic arena of continuous change, where birth and death, creation and destruction, play out on scales both vast and minute. The study of the Boomerang Nebula thus stands at the crossroads of many fields: astrophysics, chemistry, quantum physics, thermodynamics, and cosmology. Its extreme conditions serve as a touchstone for testing theories and inspire new questions about the behavior of matter and energy under conditions unattainable on Earth. As our technology advances and new telescopes come online, such as the James Webb Space Telescope, JWST, we anticipate gaining even deeper insights into the Boomerang Nebula's mysteries. High-resolution infrared observations could reveal the dust composition and temperature distribution with unprecedented detail. Spectroscopy will probe the chemical complexity, while time-domain studies may catch changes in the nebula's structure, offering a dynamic view of its evolution. In the grand tapestry of the cosmos, the Boomerang Nebula is a striking reminder of the extremes that nature can reach, challenging our imagination and expanding our knowledge. It stands as a symbol of the universe's complexity, beauty, and relentless change, inviting us to explore further and ponder the profound mysteries of space. Continuing our deep exploration of the Boomerang Nebula, it's important to consider how this celestial marvel fits into the broader context of astrophysical phenomena, particularly in comparison with other nebulae and cold cosmic environments. While the Boomerang Nebula holds the title of the coldest natural place in the known universe, the conditions there highlight a fascinating interplay between stellar evolution, gas dynamics, and thermodynamics that offers valuable insight into many other cosmic processes. One intriguing aspect is the comparison between the Boomerang Nebula and other well-studied planetary nebulae. Most planetary nebulae glow brightly in visible and ultraviolet light due to the hot, exposed core of the star ionizing the expelled gas. This creates the iconic colorful displays observed in telescopes. However, the Boomerang Nebula is in an earlier, preplanetary nebula phase, sometimes called a protoplanetary nebula, where the central star is still relatively cool and the gas is mostly neutral or molecular, emitting primarily in the infrared and radio wavelengths rather than visible light. This transitional stage is crucial for understanding how stars shed their outer layers and evolve toward the planetary nebula phase. The Boomerang Nebula's extraordinarily cold temperature also invites comparisons to man-made laboratories where scientists attempt to reach near absolute zero. On Earth, achieving temperatures close to 1 Kelvin requires sophisticated cryogenic techniques and advanced equipment like dilution refrigerators. The nebula achieves similar conditions naturally, but through a completely different mechanism: rapid adiabatic expansion of gas into the vacuum of space, without any external refrigeration. This cosmic refrigeration demonstrates nature's ability to produce extremes that push the boundaries of our understanding of physics. Exploring the molecular chemistry of the nebula opens yet another window into its unique environment. At such low temperatures, complex molecules can form and survive, which are otherwise fragile or short-lived in warmer regions of space. The presence of molecules such as carbon monoxide (CO), molecular hydrogen (H2), and other organic compounds provides important clues about the chemistry that occurs in stellar outflows. This chemistry also connects to the broader question of how prebiotic molecules, the building blocks of life, may form in space before being incorporated into planets. Moreover, the Boomerang Nebula's study enhances our understanding of how dust grains form and evolve in stellar environments. Dust is critical to many astrophysical processes, from star formation to the cooling of gas clouds and the shielding of molecules from destructive ultraviolet radiation. Observations suggest that dust grains in the nebula are coated with icy mantles, which could serve as catalytic surfaces for complex chemical reactions. These reactions may lead to the creation of organic molecules, linking the life cycle of stars to the origins of chemistry in the universe. Technological innovations in telescope design and instrumentation continue to revolutionize our ability to observe and analyze objects like the Boomerang Nebula. Instruments capable of high spectral resolution and sensitivity in the millimeter and submillimeter range have allowed astronomers to map the detailed velocity structure of the nebula's gas. This reveals not only the speed of the outflows but also subtle asymmetries and variations that hint at underlying physical mechanisms, such as magnetic fields or binary star interactions. The presence of a potential companion star is a significant consideration in explaining the Boomerang Nebula's shape and dynamics. Binary systems are common among stars, and their gravitational interactions can strongly influence mass loss processes. For instance, a companion could funnel material into focus jets or spiral arms, shaping the outflow into bipolar lobes. Detecting and characterizing such companions requires precise measurements and often indirect evidence, but their role in shaping planetary nebulae is an active area of research. In addition to astrophysical insights, the Boomerang Nebula sparks curiosity about fundamental physics. The extremely low temperatures approach conditions where quantum mechanical effects become important on macroscopic scales. For example, phenomena such as Bose-Einstein condensation, where particles occupy the same quantum state, are being studied in laboratory settings at ultra-cold temperatures. While it's unlikely that such exotic states occur on a large scale in the nebula, the parallels encourage scientists to think about how quantum mechanics might influence molecular interactions and gas dynamics in space. Furthermore, the Boomerang Nebula's temperature challenges our understanding of thermal balance in astrophysical systems. Typically, cosmic gas clouds are warmed by radiation from stars, cosmic rays, and shock waves. The nebula's ability to cool below the cosmic microwave background temperature implies a net loss of energy that exceeds all external heating sources, emphasizing the dominance of expansion cooling. This finding pushes theorists to refine models of radiative transfer, molecular excitation, and energy exchange in cold, expanding gases. From a cosmological perspective, studying the Boomerang Nebula contributes to the narrative of cosmic recycling, the continuous cycle of matter being processed through stars and returned to the interstellar medium. As stars evolve and die, they enrich the galaxy with heavier elements and complex molecules, setting the stage for new generations of stars and planetary systems. This ongoing cycle underpins the chemical evolution of galaxies and the conditions necessary for life to emerge. Looking ahead, future missions and observatories promise to expand our knowledge even further. The James Webb Space Telescope, JWST, with its powerful infrared capabilities, will peer through dust-obscured regions to reveal the nebula's innermost structures and dust composition. Meanwhile, next-generation radio arrays will provide sharper images of the molecular gas, allowing astronomers to track changes in the nebula over time and understand the dynamics of mass loss in unprecedented detail. Ultimately, the Boomerang Nebula is not just a fascinating cosmic object but a testament to the complexity and beauty of the universe. It exemplifies how seemingly simple physical laws manifest in extraordinary ways on cosmic scales, offering endless opportunities for discovery. By studying such extremes, we deepen our comprehension of the cosmos and our place within it. Let's dive deeper into the specific physical processes governing the Boomerang Nebula's extreme cold and its implications for our understanding of astrophysical phenomena. The nebula's temperature of approximately 1 Kelvin, just a degree above absolute zero, sets a unique laboratory for examining thermodynamic processes in space, particularly adiabatic cooling caused by rapid gas expansion. At the heart of this phenomenon is the process of adiabatic expansion, which occurs when a gas expands without exchanging heat with its surroundings. In the vacuum of space, the expelled gas from the dying star in the Boomerang Nebula expands so quickly that it cools dramatically. The temperature drop results from the gas doing work on its environment, expanding and losing internal energy, which translates to a decrease in temperature. This process differs from common cooling mechanisms such as radiative cooling, where gas emits photons and loses energy by radiation. In the Boomerang Nebula, adiabatic cooling dominates due to the extreme velocity and density of the outflowing gas. Observations suggest the gas is moving outward at roughly 164 km per second, an extraordinary speed that enables the rapid drop in temperature. The composition of the gas itself plays a crucial role in the nebula's cooling efficiency. Rich in molecules such as carbon monoxide (CO), the gas emits radiation at specific millimeter wavelengths that further aid in energy loss, complementing the cooling from expansion. The presence of molecules rather than ionized atoms indicates the nebula is relatively cool and dense compared to more evolved planetary nebulae. The nebula's shape, reminiscent of a bow tie or boomerang, arises from the anisotropic nature of the gas outflow. The star at the center, a dying red giant, sheds its outer layers unevenly. The equatorial regions tend to have denser, slower-moving material, while the polar regions expel gas at higher velocities. This bipolar outflow sculpts the gas into two lobes extending away from the star, forming the iconic shape seen in images. Researchers hypothesize that magnetic fields or the presence of a close binary companion may influence this asymmetric mass loss. Magnetic fields can channel and constrain the outflow, while a companion star's gravity can distort the envelope and create focus jets. These mechanisms, while challenging to observe directly, are inferred from detailed spectral and morphological studies. The Boomerang Nebula also offers clues about the late stages of stellar evolution, particularly for low to intermediate mass stars, those with masses roughly 1 to 8 times that of our Sun. Such stars end their lives not with violent supernova explosions but by expelling their outer layers into space, creating planetary nebulae and leaving behind white dwarfs. The protoplanetary phase, as represented by the Boomerang Nebula, is a fleeting stage lasting only a few thousand years, a brief moment on cosmic timescales. During this time, the star's core is exposed but not yet hot enough to ionize the expelled gas fully. This makes the nebula difficult to observe in visible light, but ideal for study in radio and infrared wavelengths. In fact, much of what we know about the Boomerang Nebula comes from radio astronomy. The Atacama Large Millimeter/Submillimeter Array, ALMA, in Chile has provided unprecedented images and spectral data, revealing the nebula's structure and dynamics in exquisite detail. ALMA's high sensitivity allows detection of faint molecular lines, tracing the motion and temperature of the gas. The discovery of the Boomerang Nebula's extreme cold was initially surprising because it challenged assumptions about the thermal environments possible in space. The temperature was measured to be below the 2.7 Kelvin cosmic microwave background radiation, CMB, which permeates all of space. Normally, the CMB sets a lower temperature limit, but the Boomerang Nebula's gas cools below this by expanding and becoming optically thick in the molecular emission lines, effectively shielding itself. This unique thermal environment prompts questions about the interplay between the nebula and the CMB. How does the gas maintain such low temperatures without warming back up from the omnipresent radiation? The answer lies in the density and optical properties of the expanding gas cloud, which absorb and re-emit radiation efficiently enough to maintain cooling. Beyond physics, the Boomerang Nebula's existence underscores the beauty of the universe's cycles of birth, death, and rebirth. The gas expelled by the dying star will eventually mix with the interstellar medium, enriching it with elements forged in the star's interior, such as carbon, nitrogen, and oxygen. These elements are the raw materials for new stars, planets, and potentially life itself. This cosmic recycling process is a cornerstone of galactic evolution, and objects like the Boomerang Nebula help us understand the mechanisms behind it. The nebula is not merely a relic of a star's death but a contributor to the ongoing evolution of its galaxy. Studying such cold environments also has implications for astrochemistry and the origins of complex organic molecules in space. The low temperatures allow molecules to survive longer and undergo chemical reactions on dust-grained surfaces, potentially forming the precursors to amino acids and other biomolecules. In this way, the Boomerang Nebula serves as a bridge between stellar astrophysics and the study of cosmic origins of life. Understanding its physical and chemical conditions provides insight into the environments where prebiotic chemistry could occur. Looking forward, advancements in observational technology and theoretical modeling will deepen our understanding of this enigmatic nebula. Missions like the James Webb Space Telescope, with its infrared capabilities, will peer through dust and gas to reveal the inner workings of the central star and its immediate surroundings. Meanwhile, improvements in computational astrophysics will allow simulations of gas dynamics, radiative transfer, and chemistry under extreme conditions like those in the Boomerang Nebula. Such models are crucial to interpret observations and predict the nebula's future evolution. The Boomerang Nebula's title as the coldest known natural place in the universe opens a window into a fascinating range of astrophysical phenomena, from thermodynamics and gas dynamics to stellar evolution and cosmic chemistry. It reminds us of the universe's capacity for extremes and the intricate processes that govern the life cycles of stars and matter. The Boomerang Nebula, with its record-breaking low temperature of just 1 Kelvin, continues to astonish and intrigue scientists not only because of its physical characteristics, but also due to the broader implications it holds for our understanding of the cosmos. In continuing our journey through this frigid and magnificent celestial body, we must now explore how this object fits into the larger context of astrophysics and what it reveals about the nature of space, time, and matter itself. At the core of the Boomerang Nebula's mysteries lies the profound question of how such an extreme environment can exist in a universe where most places are relatively warmer, especially when compared to the omnipresent cosmic microwave background radiation that pervades the entire cosmos at 2.7 Kelvin. To encounter a region of space that somehow defies this baseline temperature calls for a reevaluation of some fundamental astrophysical principles. It also compels us to ask, are there other such places hidden within the tapestry of our universe, quietly pushing the limits of what we believe possible? One significant insight offered by the Boomerang Nebula relates to the study of stellar death and the environmental conditions that surround it. As stars like our Sun exhaust their nuclear fuel, they enter the red giant phase, eventually shedding their outer layers into space. This mass loss process is not a gentle or uniform event. It is chaotic, explosive, and rich with both visual complexity and physical turbulence. The Boomerang Nebula represents a particularly violent instance of such a transformation, one where the ejected material is moving outward at speeds fast enough to trigger extreme adiabatic cooling. This rapid expansion, in effect, pulls the heat out of the gas, pushing its temperature down to a mere degree above absolute zero. These temperatures are so low that they approach a regime where atomic motion nearly ceases. At 1 Kelvin, particles have extremely low kinetic energy. The atomic and molecular behavior in such a state is vastly different from anything experienced in more familiar conditions. Scientists are particularly fascinated by this because it offers a rare opportunity to study physics near absolute zero in a natural, cosmic laboratory. Unlike laboratories on Earth that require enormous energy input and complex machinery to cool matter to such temperatures, the Boomerang Nebula does this, for free, through natural expansion in the vacuum of space. Additionally, the Boomerang Nebula teaches us about the role of molecular emissions in radiative cooling. While the rapid expansion contributes to adiabatic cooling, the molecular composition of the ejected gas, especially molecules like carbon monoxide, further assists in this temperature reduction. These molecules emit radiation at very specific frequencies, allowing them to radiate heat away efficiently. Carbon monoxide, for example, is particularly effective at this because of its strong dipole moment and ability to transition between energy states in ways that release substantial amounts of energy into the surrounding space. In effect, it acts like a molecular air conditioner, draining thermal energy from the gas cloud. This molecular radiation is not just a mechanism of cooling, it's also a treasure trove of data for astronomers. Each spectral line emitted by these molecules provides detailed information about the physical conditions within the nebula: temperature, density, velocity, and chemical composition. This allows astronomers to build precise models of the Boomerang Nebula's structure and behavior, even though it lies thousands of light-years away. What's more fascinating is that this kind of molecular emission and extreme cooling can only occur under a very specific set of conditions. It requires a dense, cold, and rapidly expanding medium, free from nearby heating sources such as ionizing radiation or supernova shock waves. The Boomerang Nebula is thus something of a cosmic rarity, a place where all these ingredients come together to produce a perfectly frozen portrait of stellar death. The nebula's unique shape also contributes to its mystique. Rather than a perfect sphere, it appears as two lobes extending outward from a central point, resembling a boomerang or an hourglass. This asymmetry indicates a highly directional flow of gas, most likely shaped by interactions between the central star and a possible binary companion. Many planetary nebulae exhibit similar bipolar structures, often caused by gravitational dynamics in binary star systems. These dynamics can channel the outflow of gas along the poles, resulting in jet-like emissions that pierce the surrounding material. The Boomerang Nebula is likely still in transition. Its central star has not yet heated up enough to ionize the ejected gas fully, meaning that it hasn't yet become a true planetary nebula in the traditional sense. This intermediate stage is known as a protoplanetary nebula or preplanetary nebula. This is a particularly brief and poorly understood phase of stellar evolution, lasting only a few thousand years, a blink of an eye in cosmic terms. Catching a star in this moment is like snapping a photograph in the middle of an explosion. It's an ephemeral, transitional state, and that adds another layer of urgency to studying objects like the Boomerang Nebula. Understanding this phase better can offer insights into the fates of countless other stars, including our own Sun. In about 5 billion years, our Sun will enter its red giant phase, and eventually it too will shed its outer layers into space, creating a similar nebula. Whether it will look anything like the Boomerang Nebula depends on various factors: its mass loss rate, the presence of planetary or stellar companions, and magnetic field dynamics. Nonetheless, by studying the Boomerang Nebula, we are, in a sense, peering into our own distant future. The location of the Boomerang Nebula in the sky is also of interest. It is situated in the constellation Centaurus, approximately 5,000 light-years from Earth. From our planet's vantage point, it is not visible to the naked eye, even though it spans more than a light-year in diameter. Its faintness results from the fact that much of its radiation is emitted in the millimeter and sub-millimeter wavelengths, rather than in visible light. Instruments like AOME, ADACOM, a large millimeter/sub-millimeter array, and the Hubble Space Telescope have provided the most detailed images and spectral data of this frozen cloud. With the help of AOME, astronomers have been able to create high-resolution maps of the nebula's molecular gas, measuring not just the position and brightness of the gas, but also its velocity and density at various points. This allows for 3D reconstructions of the nebula's structure, offering unprecedented insight into how such extreme conditions can arise and persist. One striking finding is that the Boomerang Nebula's expansion is not uniform. It seems to have multiple outflow episodes, suggesting that the central star may have undergone several bursts of mass loss, each contributing a new layer to the overall structure. Furthermore, the extreme cold found in this nebula may offer a template for similar environments in the early universe. Just after the Big Bang, the universe expanded and cooled rapidly, eventually reaching the temperature we see in the cosmic microwave background today. The Boomerang Nebula, in its chilling emptiness, mirrors that primordial cooling in a localized, observable form. By studying it, we might also gain indirect insights into the thermal history of the universe and the processes that govern the formation of the first molecules, stars, and galaxies. In the field of astrochemistry, the Boomerang Nebula is a hotbed, ironically, for studying the formation of complex molecules. The low temperatures, combined with the presence of dust grains, provide ideal conditions for atoms to stick to surfaces and undergo chemical reactions. On these tiny cosmic dust particles, hydrogen, carbon, nitrogen, and oxygen can combine to form increasingly complex organic molecules. This chemistry may eventually seed the interstellar medium with the raw ingredients necessary for life. So in a very real sense, the Boomerang Nebula, despite its coldness and apparent stillness, may be part of a much larger narrative, the cosmic story of life's origins. The idea that something as lifeless and frozen as the Boomerang Nebula could potentially contribute to the building blocks of life is one of the many beautiful ironies the universe offers us. Here we have an environment so cold that atomic motion slows nearly to a halt, yet within this deep cosmic freezer, complex chemistry may be brewing, quietly, methodically, and invisibly over thousands of years. This dual nature, of death giving rise to the seeds of future creation, reflects one of the fundamental cycles in the cosmos. Stars die and shed their elements, which become the ingredients for new stars, planets, and perhaps eventually, living beings. The Boomerang Nebula, then, may not only represent an end, it may also whisper of new beginnings. Dust grains inside the nebula are particularly crucial to this chemical evolution. These tiny particles, composed mostly of silicates, carbon, and ices, act as catalysts. In the frigid temperatures, atoms adhere to their surfaces and form molecules through slow, non-energetic interactions. Water, methane, formaldehyde, and even more complex organic molecules can form under such conditions. Over time, as the nebula ages and warms due to increasing ultraviolet radiation from its central star, these molecules are liberated into the gas phase, enriching the surrounding interstellar medium. In this way, planetary nebulae like the Boomerang play a vital role in recycling material through the galaxy. Moreover, the Boomerang Nebula forces us to reconsider the limits of temperature in the universe. For a long time, absolute zero Kelvin, was considered an unapproachable boundary, a place where all atomic motion ceases. While absolute zero remains a theoretical lower limit, the Boomerang Nebula, sitting at just 1 Kelvin, gives us a real-world example of how close nature can come to that boundary on its own. It challenges our assumptions and opens new avenues of inquiry. Could other parts of the universe harbor even colder regions? Are there mechanisms yet undiscovered that could produce sub-Kelvin environments? Interestingly, the 1 Kelvin temperature in the Boomerang Nebula was not inferred from visible light images but from careful measurements of millimeter-wave emissions. Observations showed that the radiation from the nebula was absorbing more background radiation than it emitted, effectively casting a kind of thermal shadow against the cosmic microwave background. This technique, known as inverse microwave background absorption, revealed that the temperature of the gas was lower than that of the surrounding space. It's a counterintuitive concept, that something could be so cold that it absorbs the very lowest energy radiation in the universe. But that is the level of extremity we're dealing with in the Boomerang Nebula. Such precision in measurement has only been possible thanks to advancements in observational astronomy. ALMA, in particular, has revolutionized our ability to study cold, dusty, and molecular-rich regions of space. With its array of 66 high-precision antennas located in the Chilean Andes, ALMA can resolve tiny details at millimeter and submillimeter wavelengths. This capability allows astronomers to study the temperature, velocity, and chemical composition of gas clouds with extraordinary accuracy. The Boomerang Nebula, which was once just a faint smudge in earlier telescopes, now reveals its internal structure in breathtaking detail: filaments of gas, arcs of dust, and bubbles of extreme cold. Another surprising feature of the Boomerang Nebula is how dynamic it is, despite appearing frozen in time. Its expansion continues, its central star evolves, and its structure slowly transforms. At some point in the future, the central star will grow hot enough to ionize the surrounding gas. When this happens, the Boomerang will officially become a planetary nebula in the classical sense. The cooling will cease, and the gas will heat up and glow brightly, perhaps resembling more familiar planetary nebulae like the Ring Nebula or the Dumbbell Nebula. This transition will be short-lived on cosmic timescales, perhaps just a few tens of thousands of years, after which the nebula will dissipate into space, leaving behind only a white dwarf and a legacy of molecules and dust. The presence of a potential binary star system at the center of the Boomerang Nebula is also a subject of intense study. Binary interactions are known to cause complex outflow patterns in stellar envelopes, including jets, lobes, and arcs. If a companion star exists, it may be accreting material from the primary star or influencing the directionality of the gas outflows through gravitational torques. These interactions can amplify the asymmetry of the nebula, creating the distinctive hourglass shape that we observe. Understanding the dynamics of such systems helps us model the life cycles of stars more accurately, particularly in cases where binary interactions play a dominant role. Beyond the astrophysical and chemical interest, the Boomerang Nebula also serves a philosophical and poetic role in our understanding of the cosmos. It is a place where the laws of thermodynamics, stellar evolution, and molecular chemistry all converge in a single spectacle. It reminds us of how much there still is to discover and understand in the universe. Even in regions of space that are incredibly dark, quiet, and cold, complexity abounds. Life may not exist there, but the processes that enable life elsewhere may very well begin in such unlikely places. When we think about the coldest places in the universe, we often imagine vast, empty voids between galaxies. But the Boomerang Nebula turns that assumption on its head. It is not the emptiest part of space that is the coldest, but rather a place teeming with matter that is expanding so quickly and efficiently that it loses almost all of its thermal energy. This paradox underscores a common theme in astrophysics, that the universe is often more counterintuitive than we expect. It also raises fascinating questions about time. In such a cold environment, where energy levels are so low, does the flow of time feel different? Of course, the fundamental passage of time is not directly affected by temperature, but the perception and effects of time can be. Processes slow down. Chemical reactions occur more slowly. Matter clumps or disperses over much longer timescales. In a sense, the Boomerang Nebula may be experiencing a kind of suspended animation, a brief, cold pause in the star's life cycle before the fireworks of ionization and illumination begin. In cosmic terms, it's a moment of calm before the next storm of stellar evolution. But it is a breathtakingly quiet moment. A moment so quiet, in fact, that it suppresses the very energy of space itself. As we continue to study the Boomerang Nebula with ever more sophisticated instruments, we may uncover even more secrets buried within its cold, dusty lobes. Perhaps we will find evidence of complex molecules never before seen in space. Perhaps we will learn more about the influence of binary systems on stellar death. Or perhaps we will simply marvel at its silence, its symmetry, and its staggering stillness. The Boomerang Nebula may be 5,000 light-years away, but its significance reaches into every corner of astrophysics, astrochemistry, and even the philosophy of science itself. It is, in a way, a cosmic mirror. In its extreme coldness, we find the extremities of existence. In its silence, we hear echoes of creation. In its frozen gases, we glimpse the alchemy of stars, the building blocks of planets, and the distant promise of life. This extreme, almost unearthly coldness, so frigid that it undercuts even the cosmic microwave background, isn't just a footnote in astrophysics. It's a fundamental challenge to our understanding of thermodynamics on cosmic scales. How can a natural process, one not engineered in a lab, strip energy so thoroughly from matter that it plunges below the universe's ambient temperature? The Boomerang Nebula is not merely colder than deep space. It's an active agent in that cold, a producer of sub-microwave background temperatures. Its astonishing outflows, expanding at speeds around 164 km per second, perform a kind of cosmic refrigeration. The gas rushes outward so quickly that it expands and cools before it has a chance to absorb even the faint warmth of starlight or the universe's background radiation. This insight draws us into one of the most elegant ironies in the observable universe, that motion, such a fundamental expression of energy, can result in profound stillness. That violent stellar death throes can manifest as frozen silence. It seems almost paradoxical, like a scream that cools the room into silence. But the mathematics behind it checks out. As the stellar envelope expands, its density drops. With that drop comes a decrease in collisions between particles, and with fewer collisions, there's less heat. What little internal energy remains is rapidly consumed by the sheer speed of expansion, and so the gas chills until it reaches a staggering 1 Kelvin. And this is not a local effect, not confined to a small pocket of gas. It encompasses nearly the entire nebula. That means the region of extreme coldness isn't a pinprick in space. It stretches for thousands of astronomical units. It's a vast, ghostly theater of molecular calm, where photons are so rare and so low in energy that they barely stir the molecules of gas and dust suspended in the void. If you could somehow travel there, without dying instantly, you would find yourself immersed in the closest natural analog to absolute zero that we've ever discovered. Despite this, or perhaps because of it, the Boomerang Nebula is alive with processes. These include radiative transfer, molecular rotation, photodissociation, and the onset of ionization at the fringes of the outflows. As cold as it is, this region of space is a dynamic laboratory, where stellar matter transforms. The star's outer layers, once part of a vibrant, energy-producing body, are now being stripped and sculpted into new forms. The shape they take is far from random. It is governed by pressures, thermal, radiative, and gravitational, that interplay over vast timescales. One of the more visually fascinating aspects of the Boomerang Nebula is its bilobed or hourglass shape. This structure is a strong indication that we are not witnessing a simple, spherically symmetric mass loss, as we might expect from a solitary star. Instead, the lobes point toward the presence of strong anisotropies, directional differences in the way mass is being ejected. This could be due to the rotation of the star, the influence of magnetic fields, or, most likely, the gravitational interactions of a companion star. The hourglass shape isn't just beautiful, it's a forensic clue. It's the footprint of complex gravitational ballet playing out between two ancient, dying stars. Furthermore, high-resolution observations show that the interior of the Boomerang Nebula isn't just empty or uniform. It has substructures, fine jets, ridges, ripples, and arcs. These features suggest episodic outflows, sudden shifts in the star's behavior, and maybe even explosive events. Every ripple tells a story of some internal convulsion, a thermal pulse, or a tidal disruption. These details help scientists reconstruct a timeline of events that have shaped the nebula. It's like walking into a cosmic crime scene and deducing the motive, method, and aftermath from the positions of scattered fragments. But there's more. The cold temperature of the Boomerang Nebula may also offer us clues about how to detect other such extreme environments elsewhere in the universe. Prior to its detailed study, astronomers would not have thought to look for cold by searching for thermal absorption against the microwave background. Now, this technique has opened the possibility of identifying other cold outflows, cold clouds, or even new types of interstellar phenomena previously masked by more energetic neighbors. Additionally, the Boomerang Nebula is an important case study in the life cycle of stars similar to our Sun. While it may seem exotic and distant, it is, in essence, a future portrait of what our solar system might look like billions of years from now. When our Sun exhausts its hydrogen fuel and becomes a red giant, it will begin shedding its outer layers. If a planetary or brown dwarf companion exists, it may help shape the resulting envelope into something reminiscent of the boomerang. Observing this process now gives us an eerie glimpse into the fate of our own stellar neighborhood. Moreover, this nebula deepens our understanding of how mass is recycled through the galaxy. Every molecule blown into space from the Boomerang Nebula will, over time, mix into the interstellar medium. There, it may be swept into a new molecular cloud, one dense enough to birth a fresh generation of stars. Some of those stars will form with planetary systems. Some of those planets may harbor life. And so the cycle continues. Frozen silence becomes fiery rebirth. We often think of cold as deathly, as sterile, as a cessation of movement and life. But the Boomerang Nebula shows us that even in the lowest energy environments, the cosmos still churns with creative possibility. Chemistry doesn't stop at 1 Kelvin, it just slows. And in that slow, deliberate unfolding, new molecules can form, complex structures can arise, and the next generation of stars can begin to take shape. Cold is not the end, it's a prelude. When we point our instruments at this object, we are effectively observing a slow-motion film of stellar death. Each measurement, each wavelength, each spectral line is a frame. And in that film, we see the old giving way to the new, not with fireworks and drama, but with a whispered exhalation so cold it stuns the very fabric of space. And perhaps most astonishing of all is the scale of this phenomenon. We are looking at something 5,000 light-years away, something that appears to us as a faint, ethereal smudge, and yet it contains within it the deepest natural chill known to science. It is a reminder that even the faintest signals can carry the most profound truths. This silent, frigid sculpture in the sky continues to defy expectations, inspire awe, and invite inquiry. It is a message from the cosmos, broadcast not in radio or light, but in temperature, in the absence of heat. And the message is clear: even in the coldest corners of space, the universe is never truly still. And so, as we continue our plunge into the enigma that is the Boomerang Nebula, let's return to the very heart of its scientific implications, not just as an astrophysical curiosity, but as a challenge to the boundaries of human understanding. Imagine, for a moment, the very concept of 1 Kelvin. Just 1 degree above absolute zero. At this near-zero temperature, nearly all atomic motion ceases. Thermal energy, the very lifeblood of molecular activity, is almost entirely drained. This isn't merely cold in the conventional sense, it's a state of matter where the rules begin to bend, where quantum phenomena rise to prominence, and where the classical laws of thermodynamics start to unravel. This level of cold is something scientists labor intensively to replicate in laboratories. To achieve similar conditions on Earth, researchers must deploy elaborate apparatuses, laser cooling systems, magnetic traps, and vacuum chambers designed to eliminate even the smallest stray photon. In contrast, the Boomerang Nebula does this effortlessly, as a natural consequence of stellar evolution. That simple fact, that a dying star in the remote reaches of space can outcool the most sophisticated machines on Earth, is both humbling and inspiring. It forces us to ask, how much more do we have yet to learn from the cosmos? Another deeply fascinating aspect is how this cold influences the chemistry of the nebula. At such frigid temperatures, reactions that would normally occur rapidly grind to a near halt. Yet, certain exotic processes persist. Molecules can cling together longer. Dust grains can grow, complex ices can accumulate on solid particles. These are the very conditions believed to be essential for the formation of complex organic molecules. Thus, in this deathly quiet, there may be the whispered beginnings of life itself. It is a paradox wrapped in molecular frost, that in this place so devoid of warmth, the building blocks of biology might slowly take form. This also leads to a deeper consideration of dust and molecular gas dynamics in such environments. The Boomerang Nebula, with its expanding shell of material, gives us a unique opportunity to study dust formation and survival in extreme cold. Dust grains are crucial in astrophysics. They shield molecules from radiation, act as catalysts for chemical reactions, and serve as seeds for planet formation. Observing how dust behaves under the conditions of the boomerang can tell us how efficiently stars seed the interstellar medium, and how these grains contribute to galactic recycling processes. Then there's the issue of symmetry and structure. The hourglass shape we observe hints at a larger pattern of stellar evolution seen across many dying stars. Why do so many of these nebulae, like the Hourglass Nebula, the Southern Crab, or the Butterfly Nebula, develop similar shapes? Theories point toward binary interactions, magnetic fields, or rapid rotation, but no single explanation fully satisfies. In the Boomerang, the symmetry is breathtakingly precise, suggesting an orderly process guiding the ejection of stellar material. Some believe a companion star, perhaps a white dwarf, or a small main-sequence star, may be orbiting the central progenitor, shaping its outflows into this stunning, cold masterpiece. But no companion has yet been directly observed, leaving the theory plausible, yet mysterious. We must also consider the role of carbon monoxide, CO, in studying this region. The discovery of the 1K temperature was made not through direct measurement, but through careful analysis of how the nebula absorbed background microwaves in specific molecular transitions, particularly CO rotational lines. These lines act like thermometers, giving astronomers insight into the temperature and motion of gas. The fact that CO was absorbing radiation from the cosmic microwave background indicated that the gas was colder than 2.73 K, an incredible revelation. It was, for many scientists, a moment of awe, a realization that in some far-off bubble of space, nature had created a condition colder than the very afterglow of the Big Bang. This interplay of radiation, matter, and motion makes the Boomerang Nebula a valuable testbed for computational models of stellar evolution and gas dynamics. Simulations of its outflows must account not only for the mass loss rates and initial stellar mass but for cooling curves, molecular chemistry, radiative transport, and complex three-dimensional fluid mechanics. To match observations, these models grow in complexity. They help refine our understanding of the final stages of stellar evolution, especially for intermediate mass stars. These are stars not massive enough to explode as supernovae, but not small enough to end in quiet whimpers. The Boomerang represents a dramatic punctuation mark in the lives of these stars. And what of time? The Boomerang Nebula is a relatively young nebula in cosmic terms, only about 1,500 years into its transformation. That makes it a snapshot of an early stage in the planetary nebula phase. Over the next tens of thousands of years, this frozen shell will warm as the central star heats up, eventually ionizing the gas and lighting up the structure like a beacon. What we see now is only a temporary state. In the grand arc of time, the Boomerang Nebula's icy phase is fleeting, like a frost that melts with the morning sun. To witness it now is to catch the universe in a moment of rare delicacy, a cosmic breath before the blaze. This leads us into philosophical reflection. What does it mean for the universe to have such places of coldness, places that seem to defy entropy, at least locally? The Boomerang is an illustration of a greater cosmic pattern. Extremes define the universe. Just as we find supernovae that burn with unimaginable fury, we also find nebulae that freeze into perfect stillness. The universe is a theater of contrasts. It roars and it whispers. It creates and it destroys. And in the quiet places, in the Boomerang, in the shadows of galaxies, in the cooling wakes of stars, we find the threads that bind all of these extremes together. Our study of the Boomerang Nebula continues, year after year, with new telescopes, new instruments, and new minds drawn to its mystery. Its faint glow is monitored in submillimeter arrays, infrared observatories, and radio telescopes. And each new observation yields more questions. Are there other nebulae this cold? Is the Boomerang a unique phenomenon or merely the first of its kind to be caught in the act? Could even colder regions exist, undetected, lurking in the dark matter-rich halos of galaxies or the vast voids between cosmic filaments? The future will tell. With the continued advancement of instruments like AOMA, the James Webb Space Telescope, and future missions like the Origin Space Telescope, we may discover entire families of these icy marvels. We may one day catalog them, mapping out the frigid regions of our galaxy the way we map deserts or oceans on Earth. They may even teach us new physics, new ways to understand matter, radiation, and time under the most extreme conditions. And all of it began with one peculiar object, glowing faintly in the Centaurus constellation, telling a silent story in temperature alone. As our journey into the haunting stillness of the Boomerang Nebula continues, it is important to appreciate the elegance with which nature weaves its narrative across time and space. At the forefront of this extraordinary cosmic ballet is not chaos, but a remarkable precision, one that is perhaps most evident in the formation and sustenance of the nebula's signature ultra-cold environment. The mechanism behind this frigid masterpiece is both elegant and efficient. At the heart of the Boomerang Nebula is a dying star, possibly once similar in mass to our Sun, now shedding its outer layers in a violent outburst of stellar wind. What makes this event so rare is the rate at which it is happening. The star is ejecting material at an astonishing velocity, about 164 kilometers per second. This hyperaccelerated loss of mass creates a rapidly expanding envelope of gas. And here lies the key. As this envelope expands, it cools. This is not merely cooling in the sense of getting a bit colder. No, this is adiabatic expansion at its most extreme. Adiabatic cooling occurs when gas expands in a vacuum without gaining or losing heat to its surroundings. As it expands, the molecules do less work and lose kinetic energy, resulting in a dramatic temperature drop. The Boomerang Nebula's material is expanding so fast, and so efficiently, that its temperature has dipped below that of the cosmic microwave background, the ancient whisper of the Big Bang that saturates all of space. To underscore how remarkable this is, consider this: the cosmic microwave background (CMB) has a temperature of 2.725 Kelvin. It is the coldest ambient radiation naturally present in the universe. For something to be colder than this background means it must not only be isolated from stellar heating but must be losing energy faster than it can absorb the ever-present hum of the cosmos. And yet, this tiny patch of space, enveloping a dying star 5,000 light-years away, has managed to do just that. At a staggering 1 Kelvin, it has become the universe's own cryogenic laboratory. This makes the Boomerang Nebula a critical natural experiment in the study of thermodynamics and radiation transfer. Every model of astrophysical cooling, every textbook on stellar death, must account for this incredible outlier. How much mass was ejected? Over what time frame? What are the constituents of the nebula's expanding shell? How does dust form and persist in such a freezing environment? These are not mere academic questions. They strike at the core of our understanding of how stars end their lives and how the raw materials for future stars and planets are recycled back into the galactic medium. And yet, even in its death throes, the Boomerang Nebula possesses a kind of symmetry that is hard to ignore. The hourglass shape we observe is not random. It is a testimony to physical forces acting with mathematical elegance. This shape arises because the star is not ejecting material uniformly in all directions. Instead, it is releasing gas preferentially along its poles. This bipolar outflow, combined with denser equatorial material, channels the gas into a structure that expands like the neck of a spinning top, broad at the ends, pinched at the center. What causes this symmetry? Scientists believe a binary companion may be responsible. Though no such companion has yet been directly seen, its presence would explain the shaping of the outflow. A companion star in close orbit could gravitationally sculpt the gas, pulling it into polar jets while compressing the equatorial plane. If this is true, then the Boomerang Nebula is not just a single star's swan song, but a duet, an interaction between two stellar bodies producing a cosmic sculpture of frost and light. The search for this companion continues, and with each improvement in imaging and spectrometry, we get closer to answering the question. Instruments like ALMA and JWST are capable of resolving finer and fainter structures than ever before. One day, perhaps, we will detect a wobble in the light, a flare, or a gravitational signature that confirms the existence of this hidden partner. Until then, the Boomerang holds its secret close, inviting us to look deeper. Meanwhile, the study of this nebula also informs our understanding of stellar life cycles. Our own Sun, billions of years from now, will undergo a similar transformation. It too will swell into a red giant, shed its outer layers, and leave behind a white dwarf, a dense, hot core the size of Earth but with half the mass of the Sun. It will likely form a planetary nebula, though whether it will create something as extreme as the boomerang remains to be seen. But the physics will be similar: expansion, cooling, chemistry, and the interplay of gravity and motion. In this sense, the Boomerang Nebula is a mirror, not of our present, but of our distant future. It is a vision of what lies ahead, not just for our star, but for all stars of similar mass. And as we study it, we are studying our own fate, written in starlight and sculpted in ice. Let us also consider how the boomerang affects our broader cosmological thinking. In a universe where black holes warp space-time, where quasars burn with unimaginable fury, and where galaxies collide in spectacular dances, the Boomerang Nebula stands as a quiet anomaly. It is not grand in size, nor luminous in power. It does not tear the fabric of reality, or reshape the fate of galaxies. Yet it demands our attention precisely because it defies expectation. It reminds us that the most extraordinary truths can sometimes be found in the quietest corners of the cosmos. And that is perhaps its greatest gift. The Boomerang Nebula is a symbol of humility. A dying star, unnoticed by ancient eyes, becoming the coldest place we have ever found. In its frozen heart, it holds a message not just about physics, but about wonder. That in the vastness of space, there is always something new, something unexpected, something waiting to remind us that the universe is far more complex, and far more beautiful, than we ever imagined. The Boomerang Nebula continues to captivate our scientific imagination not simply because of its record-setting temperature, but because of the questions it stirs about the fundamental workings of our universe. As we peer deeper into its icy veil, we begin to realize that it is not merely a snapshot of a dying star, it is a laboratory of cosmic processes, a place where nature experiments with extremes. It is the kind of place where conventional assumptions about space are flipped on their heads, where even the ubiquitous cosmic microwave background radiation is outdone, and where stellar death becomes not a fiery demise but a whisper into absolute silence. The implications of studying such an environment stretch far beyond stellar evolution. For instance, the chemical reactions that can take place at such ultra-low temperatures are of profound interest to astrochemists. Under normal interstellar conditions, molecules can collide with enough energy to overcome activation barriers and form more complex compounds. But at a mere 1 Kelvin, everything changes. The chemistry becomes more sluggish, more delicate, yet somehow, molecules still manage to form. This is a clue, one that suggests molecular formation in the universe may be more robust and more varied than we previously assumed. In fact, some researchers speculate that extreme cold environments like that of the Boomerang Nebula could serve as cradles for complex organic chemistry. While it might sound paradoxical, these frozen zones allow molecules to stay stable for long periods, protected from destructive high-energy radiation. Over time, these molecules might accumulate, combine, and evolve into more sophisticated structures. Could it be that such environments play a role in the broader cosmic chain that leads eventually to life? It's a stretch, but one worth considering. This question naturally leads us into the domain of astrobiology, an area of science that is growing rapidly as we discover more and more exoplanets and strange cosmic environments. Traditionally, we look for life in temperate zones, in liquid water, or in Earth-like conditions. But the universe has never cared about our assumptions. It frequently throws curveballs that make us rethink everything we know. The Boomerang Nebula is one such curveball. By showing us that extreme cold is not the end of molecular activity, but merely a shift into a different mode of physics, it hints that the parameters for potential life-bearing chemistry may be broader than we thought. Moreover, the boomerang challenges our engineering ambitions. Imagine if, someday, we wanted to build artificial cryogenic environments for spacecraft or deep space stations. The Boomerang Nebula offers a natural model for how such conditions might be achieved and maintained. It shows us that under the right circumstances, matter can reach temperatures lower than even the CMB, something once thought impossible. Could we one day harness similar processes for technological use? Perhaps not in the near future, but the lessons we draw from studying it could inform designs for cooling systems, sensors, and preservation technologies across scientific fields. But the story of the Boomerang Nebula does not stop at what we can see or measure directly. Its presence in the cosmic timeline speaks volumes about the rhythm of stellar life and death. Most stars in the universe will not die dramatic deaths in supernova explosions. Instead, like the boomerang's progenitor, they will gently shed their layers, enriching the interstellar medium with carbon, oxygen, nitrogen, and other elements crucial for forming planets and, eventually, life. The nebula, then, becomes a monument to this quieter but no less vital form of stellar recycling. And while the Boomerang Nebula is a relatively young planetary nebula, just a few thousand years into its formation, its future is already scripted in the patterns we've observed in other, older nebulae. As the stellar wind slows and the star evolves further, the rate of cooling will taper off. The intense cold may fade. The expelled gas will continue to drift into the galaxy, merging eventually with the clouds from which new stars are born. In this way, the material that once formed the Boomerang Nebula will be reincarnated, joining the endless cycle of cosmic rebirth. There's a poetic symmetry in this. The coldest place in the universe today may contribute to the warmth and brightness of a new star tomorrow. A region that now seems so still, so lifeless, may one day be the birthplace of light. It reminds us that even in death, there is purpose. Even in silence, there is a future. The more we contemplate the Boomerang Nebula, the more it transforms from a cold scientific object into something deeply philosophical. It becomes a metaphor for contrast, the coldest place created by the heat of a dying star, an hourglass that measures not just time, but entropy and transformation. It shows us that extremity and balance often exist together, and that the universe contains layers of nuance we have only begun to unravel. Let us return for a moment to its shape, the hourglass. Not only is this an aesthetic feature, but a deeply symbolic one. Time itself, the great arbiter of all things, is often depicted as an hourglass. In the case of the boomerang, the hourglass is literal, a structure carved by time and expansion, shaped by the evolution of a system heading towards its final state. But instead of sand falling downward, this hourglass spills out gas, light, and knowledge. Every year, new observations refine our understanding. The Hubble Space Telescope captured stunning optical images of the nebula, revealing its inner structure. The Atacama Large Millimeter/Submillimeter Array, ALMA, exposed the colder, denser material in extraordinary detail. Future missions, including the James Webb Space Telescope, promise to unlock even more data, infrared insights into dust, molecular chemistry, and star remnants. Each layer of data peels back more of the mystery. Is there a dense torus of material at its center? Are there dust grains forming in these low-temperature pockets? Are photonic interactions driving secondary cooling processes we haven't considered yet? These aren't idle curiosities. They are the key to unraveling how the Boomerang Nebula reached such astonishing conditions, and how long it can remain this way. And that's just it. The Boomerang Nebula is not static. It is in flux, an evolving structure that is currently at an extreme phase, a cosmic phase transition frozen in time. Someday it will warm. Someday, its symmetry will dissolve. The cold will dissipate, and the gas will disperse. But for now, we live in the rare moment where we can observe it in this incredible, fleeting state. To observe the Boomerang Nebula is to be a witness to a cosmic rarity. It is a snapshot of the universe's capacity for surprise, a challenge to our understanding of thermodynamics, a monument to the quiet grandeur of stellar death. It teaches us that silence in space is not emptiness, but complexity at a lower energy scale. It reminds us that the universe is not only vast in size but rich in the spectrum of its physical possibilities. And that, perhaps, is its ultimate contribution, not the cold, not the shape, not even the science, but the reminder that we still have so much more to learn. The cosmos is not a solved puzzle, but a living question. And the Boomerang Nebula, with its whisper-cold breath, asks us the most beautiful question of all: what else is out there, waiting to be understood? As we continue our deep dive into the enigma that is the Boomerang Nebula, it becomes clear that its mysteries are not merely technical or observational, they're existential. This peculiar object, existing approximately 5,000 light-years away in the constellation Centaurus, is more than just an observational curiosity. It's a cosmic paradox. It's colder than the background temperature of the universe itself, and that single fact forces us to confront the limits of our understanding of thermodynamics, radiation, stellar evolution, and even cosmology. Let's revisit that point again. The Boomerang Nebula is colder than the cosmic microwave background radiation, CMB. The CMB, which pervades all of space, sits at about 2.73 Kelvin, a temperature that is universally present, a relic of the Big Bang. For any region in space to fall below this temperature is not only rare, it was once thought impossible. The Boomerang Nebula, however, clocks in at an astonishing 1 Kelvin. That means its environment is just 1 degree above absolute zero, the lowest possible temperature in the universe, where atomic motion theoretically ceases. This drop in temperature happens due to the incredibly fast outflow of gas from the dying central star. The outflow is expanding at a rate of over 500,000 kilometers per hour. When gas expands rapidly, it cools. This is the principle of adiabatic cooling, something similar to how a can of compressed air becomes cold when you release the gas inside. In the case of the Boomerang Nebula, the expansion is so extreme and occurs in such a low-density environment that the heat content becomes minimal, and radiation cannot keep up. This is why the gas cools down to below the temperature of the CMB. But how is such rapid cooling even sustainable? Wouldn't the gas simply equilibrate with the surrounding universe? Surprisingly, no. The density of the expanding gas is so low that the CMB's photons don't interact efficiently with it. Without frequent collisions or incoming energy, the gas remains in its ultra-cold state for a surprisingly long duration. It is an isolated refrigerator floating in space, insulated not by barriers, but by vacuum and physics. The implications of this discovery ripple out in many directions. For physicists and cosmologists, this challenges long-held assumptions about thermal equilibrium on large cosmic scales. If other such nebulae or gas clouds exist that fall below the CMB temperature, then perhaps our models of background radiation, and its interaction with matter, need revisiting. Could there be other cold pockets in the universe hiding in plain sight, invisible because they do not radiate in frequencies we expect? For astronomers, the Boomerang Nebula becomes a case study, a cosmic classroom where we can learn about post-EGB, asymptotic giant branch, evolution, the process by which stars like our Sun end their lives. The central star in the Boomerang Nebula is likely transitioning from the AGB phase to becoming a white dwarf. This period is marked by intense mass loss, where the star ejects a significant portion of its outer layers into space. These expelled gases are what form the nebula we see today. In the Boomerang Nebula's case, this process is especially intense and asymmetric, producing the hourglass or boomerang shape and enabling the supersonic outflow that leads to the record-breaking cold. In terms of morphology, the nebula's hourglass shape is another area of intense interest. Why an hourglass? Why not spherical, like many other planetary nebulae? The most likely explanation lies in the presence of a binary companion, a hidden partner star that distorts the ejection of material. This second star, possibly orbiting closely, could channel the gas through specific paths, like jets or lobes, leading to the symmetry we observe. Magnetic fields may also play a role, guiding charged particles and shaping the expanding cloud into its current form. Observations by the Hubble Space Telescope have shown detailed, lobe structures, suggesting that the flow of material is not uniform but sculpted by internal dynamics. Let's pause here to marvel at something deeply profound. This entire nebula, this grand, frigid structure that stretches more than a light-year across, exists solely because a single star, perhaps a bit like our own Sun, reached the end of its life and began to exhale. That exhale, that final breath, didn't just scatter stardust. It sculpted a structure visible across thousands of light years. It generated conditions colder than the ambient universe. It wrote, in the void of space, a chapter of astrophysical brilliance. Now, let's zoom in closer into the chemistry. The ultra-cold gas in the Boomerang Nebula is mostly composed of molecules such as carbon monoxide, CO, which are particularly effective in tracing cold, dense gas. Observations using ALMA, the ATACM, a large millimeter/submillimeter array, have revealed highly detailed maps of the gas dynamics within the nebula. What's fascinating is how the molecular composition can tell us about the history of the star that created the nebula, its metallicity, its mass, and even its environment. In the cold heart of the nebula, where temperatures hover just above absolute zero, molecules stick to dust grains, forming icy mantles. Over time, cosmic rays or UV radiation may penetrate the outer layers, triggering complex organic chemistry even at these frigid temperatures. Laboratory experiments on Earth have attempted to recreate similar environments and have shown that such ices can indeed harbor prebiotic molecules, amino acids, hydrocarbons, and more. These findings fuel the speculation that the chemical seeds of life could originate in places like the Boomerang Nebula and eventually make their way into star-forming regions. There's also a haunting beauty to the fact that while the Boomerang Nebula is a byproduct of stellar death, it may also be a womb for future creation. The atoms released will not vanish. They will blend into the interstellar medium, enriching it with elements that future stars and planets will inherit. The carbon in our cells, the oxygen we breathe, these too were born in dying stars. The Boomerang Nebula is a snapshot of that process in action. This brings us to another point of contemplation: the timeline. The nebula's extreme coldness is not permanent. It is a transient phase. As the ejected material continues to expand, it will eventually become too diffuse to maintain such low temperatures. Interstellar radiation will gradually heat it, or at least bring it back to equilibrium with the CMB. In a few thousand or tens of thousands of years, a blink in cosmic time, the Boomerang Nebula will no longer be the coldest place in the universe. It will fade, its gases mixing with the galaxy, its central star becoming a cooling white dwarf, silently drifting through space. And yet, in the moment that we observe it, this exact moment in cosmic history, it holds a title no other place can claim. It is the coldest known natural environment, colder than deep space, colder than black hole event horizons, colder than the shadows of Pluto. That status alone makes it a monument to extremity, a frozen jewel in the tapestry of the Milky Way. As we probe further, our technological capabilities become essential. With the advent of next-generation telescopes, we will be able to study the nebula in greater detail across multiple wavelengths, from infrared to millimeter, from optical to X-ray. The James Webb Space Telescope, for instance, could pierce through the dust that currently shrouds the central star, giving us a clearer view of the mechanisms at play. Meanwhile, ground-based observatories continue to refine our measurements of outflow speeds, temperatures, and chemical compositions. But the Boomerang Nebula is not just about data, it's about inspiration. For educators, it's a vivid way to explain the life cycle of stars. For artists, it's a surreal visual, a glowing hourglass adrift in the dark sea of the galaxy. For thinkers, it's a reminder that the universe holds secrets we have yet to comprehend. And for humanity, it is a call to keep exploring, to keep asking questions, to keep building better eyes for the sky. The Boomerang Nebula stands not as an anomaly, but as a testament. It testifies to the diversity of nature's creations, to the subtlety of cosmic processes, and to the beauty that arises when physical laws interplay across time and space. It speaks in the silent language of low temperatures and high velocities, of dying stars and future worlds. And it whispers to every curious mind, there is still so much left to discover. The story of the Boomerang Nebula continues to unravel in layers, each more mysterious than the last. This celestial anomaly, discovered in 1995 by Sahai and Nyman using the Swedish ESO submillimeter telescope in Chile, defied expectations from the very beginning. Initial radio observations revealed an unusual brightness temperature, implying that the gas within the nebula was colder than the cosmic microwave background. At the time, this seemed almost too extraordinary to be real. Could a natural structure, unshielded in open space, exist at temperatures below the universal radiation bath? It was only through meticulous observation, verification, and follow-up studies that the truth of the nebula's staggering temperature, about 1 Kelvin, was accepted by the astronomical community. But what is equally fascinating is how this object has become a testbed for a wide range of astrophysical inquiries. For example, the Boomerang Nebula helps scientists explore the final stages of stellar evolution in exquisite detail. Most stars in our galaxy will die quietly, without going supernova. They will enter the red giant phase, puff out their outer envelopes, and leave behind white dwarfs surrounded by planetary nebulae. Yet the Boomerang Nebula showcases that even these quiet deaths can have dramatic, record-breaking episodes. The key lies in the rate and geometry of mass loss. Unlike spherical nebulae, the Boomerang Nebula's bipolar outflows suggest that something more complex is occurring beneath the surface. The prevailing theory involves a binary system where the interaction between two stars amplifies the dynamics of the stellar wind. This could include gravitational influences that form accretion disks, which then focus material into powerful jets. These jets could carve paths into the surrounding gas, forming the signature hourglass lobes we observe. The outflows themselves are among the fastest ever seen in planetary nebulae, exceeding speeds of 150 km per second. When gas moves that fast into low-pressure space, the cooling is extreme. The velocity, the density of space, and the adiabatic expansion combine to create a perfect cosmic cryochamber. And yet, the Boomerang Nebula is not just about being cold. It's also about transformation. It is a liminal space between the life and death of a star, a cosmic chrysalis. The very molecules that comprise the gas and dust are evolving, being broken down and reassembled by radiation. Some molecules, like CO and HCN, hydrogen cyanide, remain relatively stable in these conditions and serve as tracers. Others begin to form more complex chains, possibly contributing to the great galactic experiment of organic chemistry. Even in this coldest known place, nature is still at work, building, reshaping, and refining. What's more, the dust within the Boomerang Nebula plays a crucial role in both observation and science. Dust grains, often composed of silicates, carbon, and ice-coated particles, serve multiple functions. They reflect and scatter light, making the nebula visible in the optical spectrum, while also absorbing radiation and re-emitting it in the infrared. Dust can act as a shield for molecules, protecting them from photodissociation, and simultaneously provide surfaces for chemical reactions. In this way, the dust is not passive, it is a facilitator of cold chemistry, a cradle for molecular evolution. The images captured by the Hubble Space Telescope further revealed just how structured the nebula is. Not only is there a pronounced central hourglass shape, but within those lobes are striations, ripples, almost suggesting a history of pulsed outflows. These periodic eruptions could be the result of orbital interactions within a binary system, or possibly due to thermal pulses within the dying star. Each eruption sheds mass into space, creating a kind of layered time capsule. Each ripple holds clues to the past, its velocity, its composition, its temperature, and even the timing of its release. ALMA, Atacama Large Millimeter/Submillimeter Array, with its precision and sensitivity, offered another leap in our understanding. Through ALMA, astronomers mapped the distribution and motion of molecules in the Boomerang Nebula with high fidelity. These observations confirmed the expansion velocity, and revealed asymmetries that pointed once more to binary influence. ALMA also helped pinpoint the location of the central star, which is not directly visible in optical light due to the thick dust cocoon. By tracking gas flows, scientists could infer the center of mass and locate the buried stellar remnant. This center is key because it is the engine behind the whole system. The current theory suggests that the central star is transitioning from an AGB, asymptotic giant branch, star to a white dwarf, a path followed by all low and intermediate mass stars. During the AGB phase, the star becomes unstable, pulsing and shedding mass in significant amounts. This phase is short-lived on cosmic timescales, just tens of thousands of years, but it is among the most influential. It determines the fate of the star's envelope, the shape of the nebula, and the chemical enrichment of the galaxy. What happens during these final stages sets the stage for what kind of planetary nebula forms, and eventually, what kind of white dwarf is left behind. Even now, scientists speculate whether the Boomerang Nebula will evolve into a more typical planetary nebula or remain anomalous. Much depends on the interaction with its environment. Will it encounter interstellar material that could change its shape? Will the binary companion continue influencing the mass loss and sculpting new lobes? Or will the energy from the central star increase enough to ionize the gas, making it glow more brightly and heating it beyond the record lows we see today? These questions keep astronomers engaged, and they reveal how the Boomerang Nebula is not static. It is dynamic, ever-changing, and transitioning. What we see today is just a phase, a moment in time. Its frigid lobes will one day warm, fade, and disperse. Its star will grow dimmer and cooler. The structure that has fascinated scientists and broken thermal records will dissolve into the broader Milky Way, a whisper of its former self. Yet, long after it disappears from telescopes, its legacy will remain. The atoms it expelled will help form new stars and planets. The cold molecules, once drifting in silence, may seed life elsewhere. And the knowledge it provided, about stellar death, molecular cooling, binary dynamics, and nebular shaping, will live on in scientific literature, classrooms, documentaries, and dreams. The Boomerang Nebula, in its majestic coldness, teaches us not just about physics or chemistry, but about ephemerality. Even the coldest place in the universe cannot remain unchanged. In the void of space, where time stretches endlessly, transformation is the only constant. And perhaps that's the most poetic truth of all, that from the death of a star comes the coldest place, and from that coldest place, the raw material for life and light anew. Even as the Boomerang Nebula continues its journey through space and time, its astonishing nature continues to inspire new lines of questioning. One of the most captivating aspects is how this nebula can exist at a temperature lower than the cosmic microwave background (CMB) itself, a temperature floor that was once considered absolute. The CMB bathes the universe at a uniform 2.725 Kelvin, a relic from the Big Bang, omnipresent and unavoidable. It was long thought that nothing in the universe could naturally be colder than this ever-present thermal radiation. Yet the Boomerang Nebula shattered this notion, bringing us to the realization that under the right circumstances, extreme outflow velocities, rapid adiabatic expansion, and sufficient shielding, nature can, in its quiet, persistent way, outpace our assumptions. The implications of such a discovery stretch far beyond the beauty of the nebula itself. It challenges our understanding of thermodynamics on a cosmic scale and invites deeper consideration into how energy, or more specifically the absence of it, can behave in open space. The Boomerang Nebula effectively acts as a natural cryostat, a laboratory-sized chamber existing on an interstellar scale. What does it mean that molecules can survive, interact, and evolve in such a cold state? How do chemical processes adapt or freeze out completely at these temperatures? Could such environments contribute to the prebiotic chemistry that eventually leads to life? To answer these questions, researchers are closely examining the molecular composition of the nebula using spectroscopy. Molecular lines like CO, carbon monoxide, HCN, hydrogen cyanide, and H2, molecular hydrogen, are critical indicators of what's happening in the dark recesses of the boomerang. Observations in submillimeter and infrared wavelengths allow scientists to track these molecules' emission lines, gaining insights into their temperatures, velocities, and densities. It's in this cold, shielded cocoon that complex molecules might survive longer, unmolested by harsh radiation. Additionally, the possibility of dust-grained surface chemistry cannot be ignored. In many nebulae, these grains serve as sites for reactions that are too slow or unlikely in gas phase alone. In the cold conditions of the boomerang, ices can form: water, carbon dioxide, ammonia, and possibly even more exotic compounds. These ices can trap atoms and molecules, encouraging new bonds to form over time, ultimately creating organic molecules that are ejected into space as the nebula evolves. These organics might find their way to future star systems, becoming part of planet-forming disks, comets, or even prebiotic soups. The structure of the boomerang also continues to fascinate scientists. While it's often simplified in popular media as having an hourglass shape, the reality is far more intricate. Nested within the lobes are finer filaments, concentric rings, and jets that tell a tale of episodic eruptions. The central star, or possibly stars, appear to have undergone cycles of instability, possibly thermal pulses or mass transfer events. These events would cause a sudden shedding of material in a specific direction, creating a new ring or arc. Over time, these rings propagate outward, expanding and cooling. The result is a layered, multi-temporal structure, each part of which preserves the physical conditions of the moment it was formed, like tree rings in a cosmic forest. This dynamism is further amplified by the likelihood of a binary system at the heart of the nebula. Binary stars are known to complicate the evolution of stellar remnants. Their mutual gravitational tug-of-war often leads to mass exchange, angular momentum transfer, and disk formation. In the Boomerang Nebula, such a system could explain the symmetry and confinement of its lobes. When one star expands and begins to lose mass, the companion star can accrete some of that mass, creating jets that punch through the envelope and form channels. These jets, in turn, sculpt the surrounding material into collimated streams that stretch out into interstellar space. But the binary hypothesis does more than explain structure. It opens doors to a broader class of astrophysical phenomena. It links the Boomerang Nebula to other dramatic cosmic events, novae, X-ray binaries, and even the progenitors of Type Ia supernovae. In a very real sense, this peaceful-looking, cold nebula might be kin to some of the most energetic explosions in the universe. What separates them is a matter of timing, mass, and interaction. The Boomerang may never go supernova, but its physics echo those high-stakes scenarios. Looking further into the future of the Boomerang Nebula, we can speculate on what it will become. As the central star continues its path to becoming a white dwarf, it will eventually stop expelling mass. Its surrounding envelope, no longer replenished, will begin to thin and dissipate. The intense cold that made it famous will slowly fade as solar heating from the white dwarf begins to take hold, warming the surrounding gas. Ionization fronts may begin to propagate, lighting up the nebula in visible wavelengths and transforming it into a more traditional planetary nebula, a glowing, fading shell of ionized gas. This transformation could take thousands of years, but it is inevitable. The Boomerang Nebula's current form is a snapshot in an ongoing metamorphosis. Over the course of millions of years, even the white dwarf will grow cold and dim. The gas and dust will continue to drift into the galactic medium, mixing with other stellar remnants, contributing their molecules and atoms to future generations of stars. This is the cosmic circle of life. The death of one star provides the seeds for new beginnings. In that sense, the Boomerang Nebula is not an end, but a beginning, a promise that the universe recycles, renews, and reimagines itself constantly. And let us not forget the aesthetic wonder the boomerang evokes. From Earth, through the eyes of our most powerful telescopes, it appears not as a sterile, lifeless object, but as a beacon of mystery. The glowing lobes, the gentle striations, the shadows and highlights, all tell a story that transcends mere scientific data. They evoke awe, curiosity, and the quiet realization that we are part of a universe vast, intricate, and filled with surprises. To know that a region of space exists colder than the very background of the universe is to be reminded of how much we have yet to learn. In future missions, such as those from the James Webb Space Telescope or next-generation radio arrays, we can expect even more data on the Boomerang Nebula. Spectral resolution will improve, allowing us to identify rarer molecules, more precise thermal gradients, and perhaps even better understand the nature of the central object. If binary, what are the masses and orbits? If episodic, what triggers the bursts? These are not idle curiosities. They are the questions that shape our understanding of stellar death, galactic chemistry, and the building blocks of life. In this way, the Boomerang Nebula, though far away, plays a role in the grand cosmic narrative. It is a bridge between physics and poetry, between the frigid silence of space and the burning questions of science. And in its icy depths, it holds the memory of a star's final breath, a whisper colder than the universe itself. The Boomerang Nebula, though silent in its cold majesty, speaks volumes to those who understand the language of the stars. Its every contour, every gradient in temperature, every outflow of gas is a sentence in a cosmic storybook, a story of transformation, extremes, and mystery. As we delve deeper, we realize that even the concept of cold takes on new meaning here. On Earth, cold is relative, a weather pattern, a climate condition, a seasonal shift. In the Boomerang Nebula, cold becomes something existential, something fundamental to the architecture of matter itself. To understand the mechanisms that allow such extreme cooling, we must appreciate the concept of adiabatic expansion in cosmic environments. Adiabatic expansion refers to the cooling of gas as it expands without exchanging heat with its surroundings. In the vacuum of space, this is a perfect setup. There's essentially no external medium to conduct heat into the outflowing gas. When a star like the progenitor of the Boomerang Nebula undergoes a sudden ejection of its outer layers, this matter can be expelled at incredibly high speeds. In the Boomerang Nebula, this speed reaches around 164 kilometers per second, or more than 590,000 kilometers per hour. As this gas rapidly expands, its internal energy spreads thinly across an increasing volume, causing the temperature to plummet. But the Boomerang Nebula doesn't just cool to near CMB levels, it drops below them. This defies ordinary expectations. Why? Because under normal conditions, all objects in the universe are bathed in the CMB, and this radiation acts like a thermal floor. However, in the Boomerang Nebula, this floor is undercut by a clever cosmic twist, shielding. Dense layers of gas and dust within the nebula itself act like insulation, blocking out a portion of the CMB and allowing inner regions to become colder than this supposedly inescapable backdrop. In this way, the nebula becomes a paradox, a patch of space colder than the cosmic ambient temperature. This shielding is not uniform. Layers of dust and molecular gas vary in density and composition, and within them, a rich internal structure emerges. There are regions where carbon monoxide forms into clumps, pockets where ice may crystallize around dust grains, and voids that act as channels for outflow. These are not smooth distributions. They are chaotic and organic, driven by turbulence, magnetic fields, and the gravitational push and pull of central forces. Some regions act as sinks for infrared radiation, soaking up what little energy exists and hiding it from view. These internal complexities bring us to the broader implications of studying such a nebula. For one, it offers a window into chemical pathways that are difficult to replicate even in sophisticated laboratory settings. At such low temperatures, certain chemical reactions slow dramatically or cease altogether. Others, however, become surprisingly favorable. For example, the formation of long carbon chains or the gentle accretion of complex molecules on icy dust grains becomes more feasible. These frozen compounds may someday enrich other parts of the galaxy, carrying with them the fingerprints of their birthplace. Moreover, astronomers suspect that conditions like those in the Boomerang Nebula may be more common than previously thought. While it remains the coldest natural object ever recorded, there may be other nebulae with similar properties, yet undiscovered or simply less extreme in their characteristics. Each such discovery would expand our understanding of the life cycles of stars and the nature of interstellar matter. The Boomerang serves as a prototype, a Rosetta Stone for interpreting such enigmatic environments. From a modeling standpoint, replicating the conditions of the Boomerang Nebula requires extensive simulation. Researchers must factor in multi-phase hydrodynamics, radiative transfer, dust grain dynamics, and even quantum-level chemical kinetics. These models run on supercomputers, often generating terabytes of data just to simulate a few thousand years of evolution. By comparing these models to telescope data, especially from instruments like AOME, which captures fine-resolution sub-millimeter signals, scientists can begin to reverse-engineer the past of the Boomerang Nebula, understanding not just its current state, but how it got there. And then there is the philosophical impact of such a discovery. For millennia, humanity has associated the heavens with heat and light, flaming suns, glowing stars, radiant galaxies. The Boomerang Nebula reminds us that the cosmos is also a place of darkness and deep cold. That in the life cycle of a star, there are moments not of climax but of quiet withdrawal, of vanishing warmth. That space is not only the arena of explosions, but also of implosions, of slow fades and final exhales that whisper rather than roar. This philosophical lens can deepen our awe. The boomerang is not simply a cold object, it is a cosmic elegy, a farewell letter from a dying star. Every molecule drifting outward carries a message. I once burned, but now I give my substance to the silence. That silence is not empty, it is full of meaning, of future potential. The gas will cool, condense, and drift. It will mingle with galactic clouds. It may become part of a new solar system, a comet, or even the ocean of a habitable planet billions of years from now. In this sense, the Boomerang Nebula is not an end, but a seed. Let us also reflect on the observational challenges of such a system. Located in the constellation Centaurus and over 5,000 light-years from Earth, the Boomerang Nebula is far from easy to observe. In visible light, it is faint and unassuming, its central star obscured by a thick shroud of gas and dust. Only in specific wavelengths, particularly millimeter and submillimeter, can its true character be revealed. Instruments like ALMA, the Hubble Space Telescope, and the more recent James Webb Space Telescope play critical roles in peeling back these layers. They allow us to see not only the structure, but also to measure the temperature distribution, the speed of gas flows, and even the composition of molecules present. Despite its distance, the data we collect from the boomerang is stunningly precise. Scientists can measure the velocity of specific molecules with sub-kilometer per second accuracy. They can map temperature gradients across the lobes of the nebula and identify chemical signatures in trace concentrations. With this data, we can not only describe what the Boomerang Nebula is, we can begin to predict what it will become. And therein lies another compelling dimension of the Boomerang Nebula. It is a time machine. Not only does it preserve the memory of a star's final acts, but it also provides a blueprint for the future. By studying the boomerang, we learn more about the eventual fate of our own sun. Billions of years from now, the sun will undergo its red giant phase, shed its outer layers, and likely create a planetary nebula of its own. Whether it will be as cold or complex as the boomerang is unknown, but the process will be informed by the same physics: outflows, cooling, dust formation, and eventually silence. In its quiet, frigid way, the Boomerang Nebula challenges our understanding of what stars can do. It whispers secrets about thermal physics, stellar evolution, chemical synthesis, and even the origins of life. It reminds us that the universe is not bound by our expectations, that nature, in its infinite complexity, often writes better science fiction than we do. The journey through the coldest known place in the universe is not just a story of temperature, it's a story of life, death, and the infinite beauty of the cosmos. The Boomerang Nebula, in all its frozen majesty, is far more than a curiosity. It's a masterclass in the universe's capacity for extremes. It is here, in the chilling vacuum of space, that we confront the very limits of physical law. Where heat has fled and energy is at its lowest ebb, and yet complexity emerges. This paradox, the idea that something as structurally intricate and chemically rich as the Boomerang Nebula can arise in a place colder than the background radiation of the universe, draws scientists into a deeper philosophical and physical inquiry. We are forced to ask questions not only about the behavior of matter in extreme conditions, but also about how our own intuitions fall short in environments so foreign to human experience. Let us delve into the architecture of the nebula itself. The Hubble Space Telescope captured what appeared to be a symmetrical hourglass shape, and this was no coincidence. The double-lobed structure is not just aesthetically beautiful, it is scientifically profound. The hourglass arises from a collimated outflow, that is, jets of gas channeled through narrow regions, possibly by a rotating central star or a surrounding accretion disk. Such structures are often governed by conservation of angular momentum. As the dying star ejects material, that material doesn't simply dissipate in all directions, it's shaped, influenced by magnetic fields and rotational forces, producing the dual-lobe geometry we observe. The precision of this formation at such low temperatures is part of what makes the Boomerang Nebula such an astrophysical gem. Embedded within these lobes is a mystery, the central star. It remains obscured from direct view, swaddled in thick shrouds of dust and gas, making its properties hard to measure. But indirect evidence suggests it is a dying red giant or possibly a post-AGB, asymptotic giant branch star. This means it is at the end of its fusion life cycle, having spent most of its nuclear fuel. It's now shedding mass rapidly, and in this case, much more quickly and more violently than typical planetary nebulae progenitors. This hyperactive mass loss is precisely what causes the extraordinary cooling effect via rapid adiabatic expansion. Let's explore the science of that cooling a bit more deeply, for it is central to understanding why the Boomerang Nebula is so uniquely cold. Normally, an expanding gas cloud would cool down to a temperature that slowly equilibrates with the cosmic microwave background, which bathes all of space at approximately 2.7 Kelvin. But in the Boomerang Nebula, we find regions as cold as 1 Kelvin. This isn't just surprising, it's almost scandalous from a thermodynamic standpoint. How does a nebula lose more heat than is available to it? The answer, again, lies in shielding and rapid expansion. The gas doesn't cool because it radiates away heat. It cools because it expands so quickly that the energy within it is diluted faster than it can be replenished by external sources like the CMB. This kind of rapid expansion has only a few analogues in nature, and almost none as extreme or efficient. In terrestrial science, we simulate such conditions in highly controlled cryogenic chambers or quantum vacuum experiments, often using liquid helium or magnetic cooling methods to approach temperatures close to absolute zero. But in the Boomerang Nebula, nature achieves these same ends across trillions of kilometers with nothing more than gravity, gas, and time. This state of extreme cold introduces another fascinating wrinkle. Quantum effects begin to dominate at such low energies. In the Boomerang Nebula, it's possible that molecular motions are so restricted that quantum tunneling becomes significant. That is, particles might behave in ways counterintuitive to classical mechanics, passing through energy barriers or reacting chemically in paths that wouldn't occur at higher temperatures. For instance, molecules might form or stabilize in ways that are still poorly understood due to the peculiar quantum landscape of such frigid environments. In such regions, dust particles begin to play a central role. Dust in space isn't like the dust on your furniture. It's composed of silicates, carbon-rich compounds, icy layers, and complex organic molecules. These particles act as chemical platforms, allowing reactions to occur on their surfaces. And in the Boomerang Nebula, where gas is thin and cold, dust becomes the laboratory. Scientists believe that the icy mantles on dust grains may harbor complex molecules, even prebiotic ones. Could the seeds of life be frozen in the depths of this cosmic freezer, waiting to be transported elsewhere in the galaxy by interstellar winds? This possibility opens the door to one of the most profound implications of the Boomerang Nebula: its role in galactic ecology. Though it is currently in a phase of exhalation, its gas and dust will eventually integrate with the interstellar medium. Over millions of years, this enriched material might drift into molecular clouds, combine with other stellar debris, and become part of a new generation of stars or planets. Some of the material from the Boomerang Nebula may one day be part of the rocky core of a new world, or the frozen ocean of a distant moon. Thus, what begins as the death of a star becomes the birth cry of worlds yet unformed. From an engineering perspective, the Boomerang Nebula also serves as a point of fascination for theoretical physicists and technologists. Could we learn something from its natural cryogenics that could be applied to quantum computing or low-temperature physics on Earth? While direct applications are speculative, the inspiration is clear. Nature has engineered, without intent or design, the coldest lab in the cosmos. If we understand it, we may learn to build better labs of our own. Astronomers continue to observe the Boomerang Nebula with increasingly sensitive instruments. The James Webb Space Telescope, with its incredible infrared capability, is particularly well suited to study the cold dust and gas structures within the nebula. Its mid-infrared spectrometer allows scientists to detect specific molecular signatures, mapping where certain elements and compounds are located within the cloud. This kind of spatial chemical cartography is essential for deciphering the processes at work in the nebula's hidden core. It's also worth considering the Boomerang Nebula as a reminder of cosmic timescales. What we see today is a snapshot in a sequence that stretches over tens of thousands, even millions of years. The lobes we observe have been expanding for only about 1,500 years, a blink in stellar terms. Over time, the outflows will slow, the gas will spread out, and the nebula will cool further, eventually becoming invisible. Its star may collapse into a white dwarf, or perhaps form a binary system with an unseen companion. The cold beauty we marvel at today is a transient phase, captured in a rare moment of celestial evolution. And therein lies the poetic tragedy of the Boomerang Nebula. It is fleeting. Like a snowflake on fire, it exists in an improbable state, cold where heat should rule, structured where chaos is expected, visible where invisibility is more likely. It is a contradiction suspended in time, revealing itself only briefly before returning to the vast anonymity of space. Yet for now, we can still observe it. We can still measure its light, analyze its chemistry, model its behavior, and imagine its legacy. In doing so, we not only expand our scientific understanding, we also stretch the boundaries of human wonder. As we continue our journey into the Boomerang Nebula, the cosmic cold that it harbors continues to unfold in ways that are as baffling as they are beautiful. While the concept of 1 Kelvin, the astonishingly low temperature recorded in this nebula, might seem like just a number, its implications are profound. 1 Kelvin is just 1 degree above absolute zero, the theoretical point where all molecular motion stops. To grasp the sheer extremity of this, consider that interstellar space, considered cold by any earthly standard, is about 2.7 Kelvin due to the residual radiation from the Big Bang. And yet, the Boomerang Nebula, thanks to its rapid, supercooled outflow, is even colder. This defiance of the universal thermal floor imposed by the cosmic microwave background is not just rare, it's singular. No other naturally occurring region of space discovered so far has beaten this record. It stands alone, a quiet, chilling sentinel in the vast black of the cosmos, pushing the boundaries of what we believed nature could do without artificial intervention. The mechanisms behind this feat are as delicate as they are violent. The central star, presumed to be a dying red giant, began shedding its outer layers at a phenomenal rate. Most dying stars in the planetary nebula phase lose mass slowly and gracefully over time. But the progenitor of the Boomerang Nebula seemed to erupt in a spectacular fit of stellar weather, expelling gas at speeds exceeding 160 kilometers per second, hundreds of thousands of kilometers per hour. This sudden and violent release of material triggered the expansion-driven cooling that brought the temperature down to just above absolute zero. It's the stellar equivalent of a body violently exhaling its last breath so quickly that it freezes its own surroundings. This breath, as seen through telescopes, has sculpted the nebula into a stunning hourglass form. The twin lobes of the Boomerang Nebula are separated by a narrow waist, creating the illusion of a cosmic bow tie. These lobes are the result of bipolar outflows, jets of gas that burst forth along the poles of the star, channeled by magnetic fields, disks of dust, or possibly even the gravitational tug of an unseen binary companion. The result is symmetry within chaos, precision within entropy. As light filters through the nebula's outflow, it encounters billions of dust particles, tiny grains that absorb, scatter, and reflect the photons, often in polarized or diffused patterns. This interaction with dust is what gives the Boomerang Nebula its visible appearance in the optical and infrared bands. The visible light is actually the starlight being scattered off the walls of these hollow, expanding lobes. Meanwhile, deep inside, the thick core remains cold, dark, and largely hidden from view. The James Clerk Maxwell Telescope and the Atacama Large Millimeter/Submillimeter Array, ALMA, have played crucial roles in observing the nebula and submillimeter wavelengths, those particularly suited for studying cold gas and dust. ALMA, in particular, has revealed intricate details about the velocity of the outflows and the chemical makeup of the surrounding material. These telescopes let scientists look into the nebula's heart with an unprecedented level of clarity, allowing them to build 3D models of the gas motions and temperature distributions. Chemical analysis from these observations has unveiled a wealth of molecular complexity. Carbon monoxide (CO), hydrogen cyanide (HCN), silicon monoxide (CO), and other molecules have been detected within the Boomerang Nebula. These compounds form and survive because of the unique combination of low temperatures and moderate densities. This molecular richness is important for several reasons. it suggests active chemistry even at the lowest temperatures. It may contribute to the formation of more complex prebiotic molecules, and it helps researchers trace the history and structure of the gas outflows. Moreover, the formation and survival of these molecules point to another fascinating aspect: the protective power of the nebula's density. Although space is generally an inhospitable environment for molecules due to ultraviolet radiation and cosmic rays, the Boomerang Nebula's dense outflows act as a natural shield. These thick clouds of dust and gas absorb harmful radiation, providing a cocoon where delicate chemistry can proceed undisturbed. In a way, the Boomerang Nebula is not just a cold vacuum, it's a sheltering cradle for some of the most fragile forms of matter in the universe. Astrophysicists studying this object often invoke thermodynamic models to explain and simulate its conditions. These models must account for not only the temperature and pressure of the gas but also its velocity, density gradients, radiation transfer, and the interactions between particles. Even the dust grain size distribution becomes a variable in such simulations, affecting how light is absorbed or reflected, how molecules attach or detach, and how efficiently heat can escape. The complexity of such modeling efforts is staggering and highlights the challenges involved in fully understanding such a seemingly simple structure in the sky. The Boomerang Nebula is also a case study in stellar evolution. It represents a transitional phase, a brief period between a red giant and a fully formed planetary nebula. In this liminal stage, the star's interior is still undergoing changes. Nuclear fusion in the core has ceased or is sputtering to a halt, while the outer layers are being cast off into space. The inner core is shrinking and heating, destined to become a white dwarf, while the surrounding material will eventually glow faintly, lit by the residual ultraviolet radiation of the dying core. But that future is still hundreds or thousands of years away. Right now, we are witnessing the chaotic storm before the quiet, ghostly calm of the final nebular form. And then, there is the question of time. The Boomerang Nebula is 5,000 light-years from Earth, which means that everything we observe is already 5,000 years old. The light that now graces our telescopes began its journey around the time humans were just starting to develop complex civilizations on Earth. When we look at the Boomerang Nebula, we're not just looking across space, we're looking into the deep past. What we see may no longer exist in the same form, and yet, its story is only just being told through photons that took millennia to reach us. In the far future, as the nebula's gas continues to drift away and the central star stabilizes into a white dwarf, the coldest region in the known universe may warm slightly. It may fade from view entirely in certain wavelengths, becoming just another point of data in the interstellar archive. But for now, its existence challenges us. It urges us to rethink our assumptions about temperature, matter, motion, and time. The Boomerang Nebula is not merely an object, it's a phenomenon, a paradox, a question etched into the stars. It's the kind of thing that forces even the most seasoned scientists to pause and marvel. Because if something can be colder than the universe itself, what else might lie hidden in the cosmos, just beyond our reach? The profound cold of the Boomerang Nebula invites a deeper dive into the physics governing such an extreme environment. When we consider the laws of thermodynamics, especially in the vacuum of space, the process by which this nebula achieves a temperature of just 1 Kelvin is astonishingly instructive. Typically, temperatures near absolute zero can only be reached artificially on Earth in carefully controlled laboratory environments using sophisticated cooling techniques such as laser cooling or magnetic evaporation. Nature, however, has achieved this in a natural setting, through sheer mechanical expansion and the interplay of stellar wind and gas dynamics. To better understand this, let's focus on adiabatic expansion, the principal cooling mechanism responsible for the Boomerang Nebula's record-breaking low temperature. Adiabatic processes occur without the exchange of heat with the surrounding environment. In the nebula, this means the gas expelled from the dying star expands so quickly into the surrounding vacuum that it cools as it does work pushing against the vacuum itself. Because there's essentially nothing to conduct heat back into the gas, its temperature plummets. This rapid expansion acts like a gigantic cosmic refrigerator. Unlike typical planetary nebulae where gas expands more slowly and cools only modestly, the gas in the Boomerang Nebula rushes outward at roughly 164 km per second, much faster than in most similar objects. This high speed results in an extremely rapid drop in temperature, causing the gas to cool below the temperature of the surrounding cosmic microwave background radiation. This is not only a physical anomaly but also an astrophysical curiosity that demands detailed study. Interestingly, the nebula's name, Boomerang, comes from the shape seen in early telescope images, an hourglass or bow-tie shape reminiscent of a traditional Aboriginal boomerang. Its distinctive morphology is a direct consequence of the bipolar outflows channeled by the star's magnetic fields or possibly shaped by interaction with a close stellar companion. The symmetry is striking, revealing the elegant complexity of the physical forces at play. Observations show that these lobes extend roughly half a light-year in total size, a vast bubble of gas expanding in opposite directions. Digging further into the nature of the central star, it's likely an asymptotic giant branch, AGB star, a class of stars in the late stages of evolution. AGB stars are characterized by their immense size and pulsations, often losing mass through powerful stellar winds. Eventually, these stars shed their outer envelopes, leaving behind a hot, dense core that becomes a white dwarf. The Boomerang Nebula represents this transformative stage, but with a particularly violent mass loss episode causing the unique cooling effect. From a chemical perspective, the nebula contains not only ionized gas but also a rich collection of molecules and dust grains. The presence of molecules like carbon monoxide, CO, is crucial for astronomers because CO emission lines in the millimeter and submillimeter wavelengths serve as excellent tracers of cold gas. Observations using ALMA have detected these molecules, allowing astronomers to map the velocity and temperature structure of the nebula with remarkable precision. Moreover, dust grains composed of silicates and carbonaceous compounds contribute to the nebula's infrared emission. These grains play an important role in shielding molecules from harsh ultraviolet radiation, preserving the molecular chemistry that might otherwise be destroyed. The interplay of dust and gas creates a dynamic and complex environment where processes such as grain growth, coagulation, and even the formation of complex organic molecules could occur, offering potential insights into the early stages of molecular cloud evolution and star formation. The study of such nebulae also sheds light on the life cycle of matter in the galaxy. As stars like the progenitor of the Boomerang Nebula die, they enrich the interstellar medium with heavy elements and dust, materials essential for the formation of new stars and planets. This cosmic recycling process is fundamental to the evolution of galaxies and the chemical enrichment of the universe. One of the intriguing questions surrounding the Boomerang Nebula is whether its extreme cooling could allow exotic phases of matter or novel physical phenomena to exist. For example, at temperatures close to absolute zero, quantum effects become significant, and gases can transition into states like Bose-Einstein condensates or superfluids, states of matter rarely observed outside of terrestrial laboratories. While it is unlikely that such states currently exist on the scale of the nebula due to its low density and turbulence, the possibility invites speculation and further study. In terms of observational astronomy, the Boomerang Nebula challenges the limits of our instrumentation. Because its temperature is so low, it radiates primarily in far infrared and submillimeter wavelengths, bands of light that cannot penetrate Earth's atmosphere efficiently. This necessitates the use of space-based telescopes or high-altitude observatories equipped with specialized detectors. Missions like the Herschel Space Observatory and ALMA have been indispensable in collecting data that ground-based optical telescopes cannot provide. The nebula's extreme properties also make it a prime candidate for studying the interaction between stellar winds and the interstellar medium. Understanding these interactions can improve models of how stars influence their environments, shaping the morphology of galaxies and the distribution of matter on cosmic scales. These feedback mechanisms, while subtle, have profound implications for galaxy evolution and the life cycle of cosmic structures. On a philosophical level, the Boomerang Nebula serves as a humbling reminder of the universe's capacity to surprise. While we often think of space as a vast emptiness, it is instead a dynamic arena of extremes, where temperatures range from the blistering heat of stars to the chilling depths of molecular clouds and nebulae like this one. This diversity of conditions creates a tapestry of phenomena that fuel both scientific discovery and human imagination. In future research, astronomers hope to uncover more about the nebula's magnetic fields, which likely play a crucial role in shaping its distinctive form. Polarimetric studies, which measure the polarization of light, can reveal the alignment and strength of magnetic fields within the nebula. These fields may influence the direction and speed of the outflows, helping to explain the remarkable symmetry and the tight collimation of the lobes. Additionally, scientists are keen to monitor the nebula over time. Although changes in such distant objects occur over millennia, precise observations can detect subtle variations in brightness or structure, revealing clues about ongoing processes within the nebula. These temporal studies can bridge the gap between static snapshots and the dynamic reality of stellar evolution. Beyond its immediate scientific importance, the Boomerang Nebula has captured the public imagination, inspiring awe and curiosity. Its record-setting coldness, striking shape, and story of stellar death and rebirth resonate with broader themes of transformation and the fragility of existence. It symbolizes the universe's endless cycles of creation, destruction, and renewal. In the grand cosmic ballet, the Boomerang Nebula is both a swan song and a cold whisper, a testament to the universe's extremes and mysteries. As telescopes grow more powerful and our theoretical understanding deepens, this enigmatic nebula will continue to be a beacon, drawing us toward new horizons of knowledge and wonder. The Boomerang Nebula's unique characteristics also provide a natural laboratory for studying the fundamental physics of gas dynamics under extreme conditions. Unlike the dense and hot cores of stars where nuclear reactions dominate, the environment within the nebula is dominated by complex interactions between gas pressure, radiation, magnetic fields, and gravitational forces, all operating at near absolute zero temperatures. This opens up opportunities for astrophysicists to test theories of molecular cooling, radiative transfer, and turbulence in interstellar environments, which have implications beyond just this nebula. For instance, the interaction between the expanding gas and the ambient interstellar medium creates shock fronts, regions where the velocity of the gas abruptly changes, compressing and heating the gas locally. These shock waves are important because they can trigger chemical reactions, influence dust grain formation, and contribute to the acceleration of cosmic rays. Understanding shocks in the Boomerang Nebula therefore adds to our broader knowledge of how energy and matter propagate through space. Moreover, the nebula's rapid outflows reflect underlying processes occurring in the dying star's core. The star's pulsations and magnetic activity, combined with binary interactions if a companion star is present, can cause episodic ejections of mass. Each ejection event can differ in speed, density, and composition, leading to the intricate structures observed. Studying the layering and velocity patterns within the nebula provides clues to these past events, essentially offering a timeline of the star's final acts. The chemistry of the Boomerang Nebula is also captivating. The cold environment allows certain molecules to survive that would otherwise be broken down in hotter regions. Complex molecules like formaldehyde, ammonia, and even simple organic compounds can exist here, and they may participate in reactions leading to more complex species. This cold chemistry is not only interesting for understanding nebulae but also for exploring the origins of organic molecules that eventually seed star and planet formation. In the context of galaxy evolution, objects like the Boomerang Nebula contribute to the enrichment of the interstellar medium with heavy elements synthesized in stars. The dust and gas expelled during the star's death add to the raw materials from which new generations of stars and planets form. This ongoing cycle is fundamental to the chemical evolution of galaxies and the eventual emergence of life-supporting environments. From a technological perspective, studying the Boomerang Nebula pushes the development of advanced instrumentation. Detecting and analyzing the faint signals emitted by such cold and distant objects requires state-of-the-art sensors with high sensitivity and resolution. Improvements in radio interferometry, cryogenic detectors, and data processing techniques owe much to the challenges posed by these cosmic phenomena. Educationally, the Boomerang Nebula offers a captivating narrative for science communication. Its combination of extreme cold, stunning visuals, and stellar life cycle context makes it an excellent tool for engaging audiences with astrophysics. It highlights the interconnectedness of physical laws, chemistry, and cosmic evolution in a single, accessible example. Looking forward, upcoming missions like the James Webb Space Telescope, JWST, and the next generation of ground-based observatories will likely uncover even more details about this enigmatic nebula. Higher resolution imaging, combined with broader spectral coverage, will allow astronomers to dissect its structure, composition, and dynamics with unprecedented clarity. These observations may reveal surprises that challenge existing models or uncover new phenomena. The Boomerang Nebula stands as a remarkable natural phenomenon, the coldest known place in the universe at about 1 Kelvin. Its discovery and ongoing study illuminate processes at the extremes of temperature and physical conditions, enriching our understanding of stellar evolution, molecular astrophysics, and the life cycle of matter in the cosmos. As we continue to unravel its mysteries, the nebula reminds us of the universe's boundless capacity to surprise and inspire. The Boomerang Nebula's chilling environment invites an exploration of the subtle interplay between thermodynamics, quantum physics, and cosmic phenomena that govern such an extreme state. The near-absolute zero temperature of approximately 1 Kelvin, just 1 degree above the absolute zero limit where molecular motion theoretically ceases, places this nebula in a realm where classical physics begins to intertwine with quantum effects. While the nebula's low density and turbulent conditions mean it does not form exotic quantum states like Bose-Einstein condensates, the implications of such low temperatures remain a captivating frontier. The quantum mechanical behavior of gases at these temperatures, although faint, contributes to unique emission signatures. Molecules vibrate less, resulting in narrower spectral lines that astronomers use to infer temperature and composition. This makes the Boomerang Nebula a natural calibrator for molecular physics in space, helping refine models that interpret signals from cold molecular clouds elsewhere in the galaxy. The physical structure of the nebula is a direct consequence of its dynamic evolution. Its bipolar shape, 2 lobes extending in opposite directions, points to highly directional ejection of material, likely influenced by the star's magnetic field and possible binary companions. Magnetic fields, though invisible, leave an imprint by shaping gas flows and aligning dust grains, which polarize light passing through the nebula. Measuring this polarization offers insights into the strength and configuration of these fields, which in turn inform theories about star death and nebular formation. Moreover, the Boomerang Nebula's distance from Earth, approximately 5,000 light-years, positions it within our Milky Way galaxy's outer regions. This remoteness means the light we observe today left the nebula millennia ago, providing a window into the past. Such cosmic time travel allows astronomers to piece together stellar evolution timelines and understand how stars like the Boomerang's progenitor contribute to galactic ecology. The nebula's extreme cold also offers a striking contrast against the cosmic microwave background radiation, CMBR, the faint afterglow of the Big Bang at about 2.7 Kelvin. Remarkably, the Boomerang Nebula's gas is colder than this relic radiation, making it the only known natural object in the universe that outcools the CMBR. This phenomenon occurs because the gas expands so rapidly and cools adiabatically, without absorbing significant external radiation. This unique feature elevates the nebula as a cosmic anomaly and a topic of considerable astrophysical interest. Understanding the Boomerang Nebula extends beyond academic curiosity. It feeds into our comprehension of how matter transitions between different states in space, and how stars sculpt their surroundings in their final evolutionary phases. The interplay of stellar winds, radiation pressure, gravity, and magnetic forces shapes the nebula's intricate morphology, revealing the complex physics that govern stellar death throes. Furthermore, the chemical richness within the nebula offers clues about the origins of complex molecules in space. Cold environments like this protect fragile molecules from photodissociation, allowing them to survive and evolve. Studying these molecules not only informs astrophysics but also astrobiology, as complex organics are considered precursors to life's building blocks. In recent years, advances in observational technology have enhanced our ability to probe the Boomerang Nebula's secrets. Instruments aboard the Atacama Large Millimeter/Submillimeter Array, ALMA, and the Herschel Space Observatory have mapped the nebula's gas distribution, velocity fields, and temperature gradients with unprecedented resolution. These data have confirmed the rapid expansion velocities and detailed the cold molecular gas components responsible for its ultra-low temperature. Looking ahead, the next generation of telescopes promises even deeper insights. The James Webb Space Telescope's infrared capabilities will enable observations of dust and molecules hidden from optical telescopes. Combined with ground-based radio arrays, these instruments will build a more comprehensive picture of the nebula's physics, chemistry, and evolution. On a grander scale, the Boomerang Nebula exemplifies the life cycle of matter in the cosmos. The star at its center is shedding its outer layers, enriching the interstellar medium with gas and dust that will eventually coalesce into new stars, planets, and possibly life. This continuous recycling underscores the dynamic and interconnected nature of the universe. In essence, the Boomerang Nebula is a cosmic enigma, a freezing testament to the extremes achievable in nature and a beacon guiding our understanding of stellar evolution, molecular chemistry, and galactic ecology. Its study not only unravels the mysteries of one of the coldest places in the universe but also deepens our appreciation of the complex and beautiful processes that govern the cosmos. The Boomerang Nebula's extreme cold and unique characteristics have also inspired theoretical models that delve deeply into the thermodynamics of expanding gases in astrophysical contexts. Unlike typical nebulae, where temperature gradients arise from stellar radiation heating the surrounding gas, the Boomerang Nebula's temperature plummets due to rapid, adiabatic expansion. This expansion causes the gas to cool as it does work on its surroundings, similar to how a compressed gas cools upon release in a laboratory setting but on an immense, cosmic scale. Scientists have sought to quantify this cooling effect through detailed hydrodynamic simulations, incorporating factors such as gas density, velocity fields, molecular composition, and magnetic forces. These models strive to reproduce the observed temperature of approximately 1 Kelvin and the nebula's distinctive bipolar shape. The complexity lies in balancing the energy losses due to expansion with the heating from residual stellar radiation and cosmic rays permeating space. Another captivating aspect is the nebula's morphology, reminiscent of a bow tie or a boomerang, hence its name. This shape likely results from anisotropic mass loss, mass being expelled preferentially along certain axes, influenced by the star's rotation and magnetic field configuration. Such directional ejections suggest that the progenitor star might be part of a binary system, where interactions with a companion star create gravitational torques shaping the outflows. Moreover, the interaction between the ejected gas and the interstellar medium, ISM, creates shock fronts and instabilities that sculpt intricate filamentary structures within the nebula. Observations reveal knots, arcs, and shells of gas and dust, each bearing the imprint of dynamic processes over time. These features tell a story of the star's mass loss history and offer clues about how material is recycled into the ISM. The chemical environment inside the Boomerang Nebula is particularly intriguing. The ultra-cold temperatures allow certain molecular species to survive that would otherwise dissociate in hotter environments. Studies have detected molecules such as carbon monoxide (CO), which acts as a primary coolant through its rotational transitions. The presence of CO and other molecules serves as a diagnostic tool, enabling astronomers to estimate temperatures, densities, and gas velocities. These molecules also play a crucial role in cooling the gas further by radiating away energy, thus sustaining the nebula's low temperature. In this sense, the Boomerang Nebula is a natural laboratory for astrochemistry, revealing how molecules behave and interact in extreme environments far from the conditions on Earth. In addition to CO, dust grains within the nebula absorb stellar radiation and re-emit it at infrared wavelengths. These dust grains, composed of silicates and carbonaceous materials, influence the nebula's thermal balance and contribute to its overall energy budget. The interplay between dust and gas affects the nebula's evolution and can lead to the formation of complex organic molecules, which are essential precursors to prebiotic chemistry. From an observational standpoint, The Boomerang Nebula challenges astronomers to develop innovative techniques to measure faint signals at millimeter and sub-millimeter wavelengths. Facilities like ALMA excel in this domain, providing high-resolution maps that reveal the fine-scale structure and kinematics of the nebula. Such detailed observations allow for comparisons with theoretical models, testing our understanding of gas dynamics and thermodynamics under extreme conditions. Furthermore, the nebula's discovery and ongoing study highlight the importance of international collaboration in astronomy. Observatories around the world contribute complementary data, enabling a multi-wavelength approach that spans radio, infrared, and optical regimes. This synergy enhances the fidelity of our cosmic maps and deepens our comprehension of phenomena like the Boomerang Nebula. Beyond its astrophysical significance, the Boomerang Nebula serves as a profound reminder of the universe's capacity for extremes. Its near-absolute zero temperature exists in stark contrast to the searing cores of stars or the blazing surfaces of planets. This diversity of conditions underscores the richness of cosmic environments and the delicate balance of physical laws that govern them. As we continue to probe the Boomerang Nebula, we gain not only insights into the fate of dying stars but also a broader appreciation for the processes that recycle matter, drive chemical complexity, and shape the evolution of galaxies. Each discovery within this frigid nebula adds a vital piece to the grand puzzle of the cosmos. The Boomerang Nebula thus stands as a beacon, both literally and figuratively, in the night sky, inviting astronomers and enthusiasts alike to marvel at its beauty and ponder the mysteries it embodies. Its chilling embrace teaches us about the fragile and transient nature of cosmic phenomena, while its complex physics challenges and enriches our scientific understanding. The Boomerang Nebula is more than just the coldest place in the known universe. It is a dynamic, evolving entity that offers profound insights into stellar death, molecular astrophysics, thermodynamics, and cosmic recycling. Its study embodies the spirit of exploration and discovery that defines modern astronomy, pushing the boundaries of knowledge and inspiring future generations to look upward with wonder. The significance of the Boomerang Nebula reaches beyond its extraordinary temperature. It encapsulates the life cycle of stars and the transformation of matter in the cosmos. Stars like the Boomerang's progenitor spend the majority of their lives fusing hydrogen into helium in their cores. As they exhaust their nuclear fuel, they undergo dramatic changes, swelling into red giants or supergiants and ultimately shedding their outer layers. This shedding process is essential because it returns enriched material to the interstellar medium, seeding future generations of stars and planets. In the case of the Boomerang Nebula, this shedding manifests as a high-speed outflow of gas expanding at roughly 164 km per second, about 360,000 miles per hour. This rapid expansion results in adiabatic cooling, the process where gas cools due to its own expansion rather than from loss of heat to surroundings. Because the nebula's gas expands so quickly and remains relatively isolated from external heat sources, its temperature plummets well below that of the cosmic microwave background, making it an extreme astrophysical exception. This phenomenon illustrates principles of thermodynamics on a cosmic scale. In everyday life, we observe gases cooling when they expand in engines or refrigerators, but the Boomerang Nebula takes this concept to an extraordinary limit. The sheer scale, speed, and duration of expansion turn the nebula into a natural refrigerator, creating a unique laboratory for understanding cooling mechanisms in space. The nebula's bipolar, hourglass shape also reveals clues about the star's final moments. This shape is common in many planetary nebulae and suggests a complex interplay of forces. Rapid stellar rotation, magnetic fields, and potentially a binary companion likely direct the ejection of material preferentially along two poles. Such directional mass loss influences the future evolution of the nebula and contributes to its detailed, symmetrical form. Magnetic fields, though invisible, exert significant influence. They can channel gas flows and help maintain the shape of the nebula over time. Polarimetric observations, measurements of light polarization, reveal how dust grains align with magnetic fields, offering indirect clues about their configuration. Understanding these magnetic fields helps scientists decode how stars lose mass and how nebulae evolve. The Boomerang Nebula also plays a vital role in the chemical evolution of the galaxy. The cold temperatures protect fragile molecules from destruction, allowing complex chemistry to occur. Observations reveal the presence of molecules such as carbon monoxide, CO, and other simple compounds. These molecules are fundamental building blocks for more complex organic molecules, some of which are considered precursors to life. Dust grains in the nebula, formed from elements produced during the star's life, absorb stellar radiation and re-radiate it in the infrared. This dust not only shapes the nebula's appearance but also participates in cooling the gas and serves as a surface for chemical reactions. Studying these dust grains gives insights into the life cycle of cosmic dust, which plays a key role in star and planet formation elsewhere. Technological advances have revolutionized our understanding of the Boomerang Nebula. Observatories like AOME, ATACM, a large millimeter/submillimeter array, have provided detailed images revealing the nebula's structure, temperature distribution, and expansion velocity with unprecedented clarity. These data help test and refine theoretical models, improving our grasp of the complex physics governing nebular dynamics. The Boomerang Nebula is not just a static image, but a dynamic system evolving over thousands of years. By studying its expansion and changes, astronomers gain insight into the timing and mechanisms of stellar death, which informs broader astrophysical theories about the life cycle of stars in the galaxy. Moreover, the nebula's interaction with the surrounding interstellar medium generates shock waves and instabilities that sculpt its intricate structures, revealing a constantly changing environment. These interactions highlight the interconnectedness of cosmic objects and processes. Beyond its scientific intrigue, the Boomerang Nebula captivates the imagination. Its ethereal glow, frozen temperature, and graceful shape evoke a cosmic ballet, where forces of nature play out on a grand scale. It reminds us of the universe's capacity for extremes and the delicate balance between creation and destruction. In contemplating the Boomerang Nebula, we also consider humanity's place in the cosmos. The material expelled by dying stars like this one will one day contribute to new stars, planets, and possibly life forms. The nebula represents a stage in the continuous cosmic cycle of matter and energy, connecting the death of one star to the birth of others. This profound connection enriches our understanding of existence and underscores the importance of exploring and preserving knowledge about such remarkable phenomena. The Boomerang Nebula, as the coldest natural object known, stands as a monument to the universe's complexity, inspiring curiosity and scientific inquiry. In essence, the Boomerang Nebula offers a window into some of the most fundamental processes shaping our galaxy and universe: stellar evolution, molecular chemistry, thermodynamics, and cosmic recycling. It embodies the interplay of forces and matter, from the smallest molecules to the vast expanse of space, inviting endless exploration and discovery. The Boomerang Nebula's story extends even further when one contemplates the cosmic timeline and the ultimate fate of its central star. This dying star, no longer capable of sustaining nuclear fusion, has cast off its outer layers, creating the stunning nebula we observe. What remains is destined to become a white dwarf, a dense, slowly cooling stellar remnant approximately the size of Earth but containing the mass of our Sun. This transformation marks the final evolutionary stage for stars of this type, signaling the end of a dramatic life cycle. But the Boomerang Nebula itself will not remain in its current form indefinitely. Over thousands of years, the expanding gas will gradually dilute, mixing with the interstellar medium and enriching the galaxy with the chemical elements forged within the star. Elements like carbon, oxygen, nitrogen, and heavier metals are essential ingredients for forming new stars, planets, and eventually, the complex chemistry that underpins life. In a broader cosmic context, the Boomerang Nebula illustrates a critical phase in the galactic ecosystem. The cycle of star birth, evolution, and death sustains the chemical diversity of the universe. Each nebula formed from a dying star is a cradle for the next generation, propagating matter and energy through the vastness of space. The ultra-cold temperature of the Boomerang Nebula also has implications for our understanding of the universe's thermal background. The cosmic microwave background (CMB) radiation, a relic from the Big Bang, bathes the universe at about 2.7 Kelvin. The Boomerang Nebula's temperature, measured at approximately 1 Kelvin, is significantly colder than this background. This fact initially surprised astronomers because it implies the nebula is cooler than the ambient radiation filling space, an unusual and exceptional condition. This is possible due to the nebula's rapid adiabatic expansion, which effectively cools the gas faster than it can absorb heat from the CMB or other external sources. Studying this phenomenon helps refine our understanding of thermodynamics in space and contributes to knowledge about how temperature variations can occur in interstellar environments. Beyond astrophysics, the Boomerang Nebula challenges our imagination and perception of temperature extremes. On Earth, temperatures can plummet to around -273 degrees Celsius, 0 Kelvin, known as absolute zero, the theoretical point where particles have minimum possible energy. The Boomerang Nebula hovers near this cosmic limit but remains a natural, dynamic system rather than a laboratory-controlled environment. Its existence broadens the scale at which we consider cold and heat, stretching human understanding beyond terrestrial experience. The nebula's discovery and ongoing research reflect the interplay of observation, theory, and technology in astronomy. Instruments like ALMA and the Hubble Space Telescope have provided data across the electromagnetic spectrum, revealing intricate details that were once inaccessible. These observations allow scientists to test predictions, refine models, and push the boundaries of cosmic knowledge. Moreover, the Boomerang Nebula serves as an inspiring example of nature's extremes, demonstrating that the universe holds conditions far beyond our everyday reality. It is a testament to the diversity and wonder inherent in cosmic phenomena, reminding us that exploration and curiosity drive scientific progress. In future decades, advancements in observational technology and computational modeling will likely unveil even more secrets of the Boomerang Nebula. Higher resolution imaging, more sensitive spectroscopy, and improved theoretical frameworks will deepen insights into its composition, structure, and evolution. As humanity ventures further into space, understanding objects like the Boomerang Nebula will be essential. These nebulae serve as markers of stellar evolution and chemical enrichment, crucial for piecing together the history and future of our galaxy. The Boomerang Nebula stands as a silent, frozen monument in the cosmos, a place where temperatures reach near absolute zero, where the remnants of a dying star expand outward in a delicate dance shaped by physics and time. Its ethereal glow and extraordinary cold invite contemplation about the vastness and variety of the universe, offering endless opportunities for discovery and wonder. The Boomerang Nebula's place in the cosmic tapestry is further enriched by its role in the study of molecular astrophysics. The extreme cold allows molecules to survive in conditions where they would normally be broken apart by radiation or collisions. This unique environment serves as a natural laboratory for scientists to explore the formation and behavior of molecules in space, especially under ultra-low temperature conditions. Molecules such as carbon monoxide, CO, hydrogen cyanide, HCN, and various complex organic compounds have been detected within the nebula's expanding envelope. The presence of these molecules is significant because they are building blocks for more complex chemistry that can lead to prebiotic molecules, essential ingredients for life. By studying the Boomerang Nebula, astronomers gain insights into the chemical pathways and processes that occur in the coldest reaches of space, potentially illuminating steps that may lead to the origin of life in other parts of the universe. The nebula's dust grains also contribute to this chemical richness. Formed from elements expelled during the star's late stages, dust provides surfaces where molecules can form and react. The interaction between dust and gas in the nebula influences its thermal balance and chemical evolution, helping to regulate temperatures and protect delicate molecules from destructive radiation. Additionally, the shape and structure of the Boomerang Nebula have intrigued scientists studying the effects of stellar winds and magnetic fields on nebular morphology. The bipolar, hourglass figure arises from complex dynamics involving fast-moving winds from the star colliding with slower-moving material ejected earlier. This collision creates shock fronts, sculpting the nebula into its distinctive form. Magnetic fields, while invisible, are thought to play a role in channeling these outflows, helping maintain the nebula's shape over time. Observations using polarization measurements of light scattered by dust reveal patterns consistent with magnetically influenced structures. These findings offer clues about the magnetic environment around dying stars and how such fields influence the fate of expelled material. Furthermore, the Boomerang Nebula provides a rare example to study the adiabatic cooling process in a natural setting. Unlike laboratory refrigeration systems, this cooling occurs purely through expansion in a vacuum. The gas expands rapidly, its internal energy decreases, and its temperature drops significantly. This phenomenon highlights fundamental principles of physics operating on cosmic scales and provides a unique test case for thermodynamic models and astrophysics. The Boomerang Nebula also sparks curiosity about the fate of similar cold nebulae throughout the universe. Are there other objects even colder or exhibiting similar extreme conditions? How do these ultra-cold regions contribute to the broader galactic environment? Such questions drive ongoing observational campaigns and theoretical research, pushing the frontiers of what we know about the cosmos. The human quest to understand the Boomerang Nebula exemplifies our broader desire to comprehend the universe's extremes: temperature, density, pressure, and time scales far beyond ordinary experience. It shows how even the coldest, darkest corners of space hold profound stories about matter, energy, and the cycles of stellar life and death. As new technologies emerge, including next-generation telescopes and space missions, they will undoubtedly reveal deeper layers of complexity and beauty within the Boomerang Nebula. These advances will allow astronomers to probe the nebula's molecular composition with finer detail, map its magnetic fields with greater precision, and observe its evolution over time more clearly. The Boomerang Nebula is not merely a cold place in space. It is a dynamic, evolving cosmic entity that bridges the life cycle of stars, the chemistry of molecules, the physics of gases, and the grand narrative of the universe's ongoing transformation. Its study enriches our understanding of fundamental processes shaping the cosmos and highlights the interconnectedness of phenomena from the microscopic to the galactic scale. The nebula stands as a stark reminder that the universe is a place of extremes and wonders, where the very coldest corners are alive with activity, shaping the materials and conditions that might one day give rise to new stars, planets, and possibly even life. The Boomerang Nebula's chilling environment challenges not only our understanding of astrophysics, but also the limits of what we perceive as habitable or life-sustaining conditions. Although the nebula's temperature is near absolute zero, it offers a cosmic contrast to the regions where stars and planets form, where temperatures and energies are much higher. This extreme juxtaposition allows scientists to study how matter behaves under vastly different thermal conditions, providing insights that might influence theories about the origins of life and the potential for habitability elsewhere in the universe. For example, the preservation of fragile molecules in such a cold environment suggests that similar regions in molecular clouds, where new stars and planetary systems are born, may serve as reservoirs of complex organic compounds. These cold reservoirs could shield molecules from radiation damage, enabling them to persist long enough to participate in the chemistry that eventually leads to the formation of life-essential molecules. Hence, studying the Boomerang Nebula indirectly informs astrobiology, the field that seeks to understand the conditions for life beyond Earth. Moreover, the nebula's expanding gas also serves as a catalyst for chemical reactions. As the gas moves outward and cools, it undergoes changes in pressure and density, which can affect the rates of molecular collisions and reactions. This dynamic environment creates a complex chemical laboratory where molecules form, evolve, and sometimes break apart, contributing to the diversity of interstellar chemistry. Another fascinating aspect of the Boomerang Nebula is its place in the context of stellar evolution. The central star is at a transitional phase called the protoplanetary nebula stage, which lasts only a few thousand years, a mere blink in cosmic terms. During this phase, the star sheds its outer layers and prepares to become a planetary nebula, where ultraviolet radiation ionizes the expelled gas, causing it to glow brightly. This brief window provides astronomers a rare opportunity to study the processes that shape the final stages of a star's life. The Boomerang Nebula, with its unique temperature profile and morphology, offers clues about how stars lose mass and how the interplay of winds and magnetic fields governs the formation of complex nebular shapes. Understanding these processes is crucial because they determine how much material is returned to the interstellar medium and influence the chemical makeup of future generations of stars. The nebula's name itself evokes curiosity. Named for its distinctive boomerang shape, the nebula's form is a result of asymmetrical mass loss from the central star. This shape stands in contrast to the spherical shells typical of many other planetary nebulae, indicating that multiple factors, stellar rotation, magnetic fields, binary companions, may be at work in sculpting such structures. The Boomerang Nebula has also been a key target for multi-wavelength astronomy. Observations span from radio waves, which detect cold molecular gas, to infrared light, revealing dust emission, to visible and ultraviolet light, which show ionized gas and later evolutionary phases. Each wavelength uncovers a different facet of the nebula's complex structure and composition, enabling a more comprehensive understanding of the physical conditions present. In recent years, advanced telescopes like ALMA have provided unprecedented detail of the nebula's molecular gas distribution, velocity, and temperature. These high-resolution observations reveal the intricate interactions within the nebula, including shock fronts where fast stellar winds collide with slower-moving gas. Such shocks heat and compress the gas, affecting its chemistry and dynamics, and contributing to the nebula's evolving shape. The extreme cooling seen in the Boomerang Nebula also has parallels in other astrophysical phenomena, such as the early universe's cooling after the Big Bang or the conditions inside cold molecular clouds where stars form. By studying this nebula, astrophysicists can test theories about cooling mechanisms, radiative transfer, and gas dynamics under conditions not replicable on Earth. Furthermore, the Boomerang Nebula highlights the importance of interdisciplinary collaboration in astronomy. Chemists, physicists, and astronomers work together to interpret observations and model the nebula's complex behavior. Advances in computational astrophysics allow simulations of gas expansion, cooling, and chemical evolution, helping researchers visualize and understand processes unfolding over thousands of years. Looking ahead, the study of the Boomerang Nebula may provide valuable lessons for interpreting observations of similar cold objects discovered in other galaxies. As telescope sensitivity improves, astronomers expect to find more ultra-cold nebulae, each offering unique insights into the life cycles of stars and the chemical enrichment of the cosmos. The Boomerang Nebula is much more than just the coldest place in the known universe. It is a dynamic laboratory where physics, chemistry, and cosmic history converge. It tells a story of stellar death and rebirth, molecular survival and transformation, and the interplay of forces shaping the universe on grand scales. Its chilling temperature and haunting shape captivates scientists and enthusiasts alike, reminding us that even in the coldest corners of space, the cosmos is vibrant, evolving, and full of wonder. The Boomerang Nebula's existence also raises fundamental questions about the balance of forces in the cosmos, particularly regarding how matter interacts with radiation and magnetic fields under extreme conditions. At such low temperatures, around 1 Kelvin, just 1 degree above absolute zero, the typical kinetic energy of particles is minimal. This means that the atoms and molecules in the nebula move extraordinarily slowly compared to warmer regions of space, affecting everything from chemical reaction rates to the way light interacts with matter. One of the intriguing outcomes of this low-energy environment is the formation of complex molecules that might otherwise be too fragile to survive in warmer or more irradiated regions. The Boomerang Nebula thus acts as a cosmic freezer, preserving these molecules and allowing scientists to analyze the molecular inventory in a state that is close to primordial or pristine. These molecular signatures help unravel the history of the star's life cycle and the chemical enrichment of the surrounding interstellar medium. The precise mechanisms that cause such dramatic cooling in the Boomerang Nebula involve the physics of gas dynamics and thermodynamics on cosmic scales. When the central star expelled its outer layers, the gas moved outward rapidly, expanding into the vacuum of space. As the gas expands, it does work against its surroundings but loses internal energy, which leads to cooling, a process known as adiabatic expansion. This is similar to how the air cools in a rapidly expanding gas from a compressed container, but on a vastly larger and more intense scale. Additionally, radiation from the star plays a nuanced role. While the star's radiation can heat nearby gas, the outflowing gas at the nebula's outer edges becomes so diffuse that it no longer absorbs significant radiation, allowing it to cool unchecked. This delicate balance between heating and cooling processes is what sustains the nebula's extreme cold, making it an extraordinary natural laboratory for testing our understanding of astrophysical cooling. Another aspect worth delving into is the nebula's morphology. The hourglass shape, resembling a boomerang, results from asymmetric ejection of material from the dying star. Unlike a uniform, spherical shell, the nebula's lobes expand in a directional manner, possibly influenced by the star's rotation axis or the presence of a companion star. Some astronomers propose that binary interactions, where two stars orbit closely, can lead to such asymmetrical outflows, as the companion star's gravity shapes the mass loss. This bipolar shape influences the dynamics of the nebula's gas and dust, guiding how the cold material spreads and interacts with the surrounding interstellar medium. The central region may also harbor a dense torus or disk of material, which further confines and directs the outflows. Such structures have been observed in other protoplanetary nebulae and planetary nebulae, supporting the idea that complex geometries are common in the final stages of stellar evolution. The Boomerang Nebula's study has also been critical in understanding the end-of-life processes of low to intermediate mass stars, roughly those with masses between 1 and 8 times that of our Sun. These stars do not end their lives in supernova explosions but instead shed their outer layers gradually, enriching space with elements like carbon, nitrogen, and oxygen, elements vital for the chemistry of life. As the star sheds these layers, it moves toward the planetary nebula phase, where the exposed hot core emits ultraviolet radiation that ionizes the expelled gas, causing it to glow visibly. Observing the Boomerang Nebula offers a snapshot of this transition before the ultraviolet radiation dominates, making it a key stage in understanding how stars contribute to the galactic ecosystem. Moreover, the extreme conditions in the Boomerang Nebula provide important clues about dust grain formation and evolution. Dust grains form in the cooling gas expelled from the star and can grow through accretion and coagulation. These grains influence the nebula's opacity, thermal balance, and chemistry. They also serve as seeds for planet formation in other regions of space, so understanding dust production in evolved stars links directly to the broader story of how planets and life-supporting environments come into being. Research on the Boomerang Nebula has benefited enormously from multidisciplinary approaches combining observational astronomy, theoretical modeling, laboratory astrophysics, and chemistry. Telescopes operating at millimeter and sub-millimeter wavelengths have been especially useful because they can detect emissions from cold molecular gas and dust that are invisible at optical wavelengths. In parallel, laboratory experiments simulate the low-temperature chemistry occurring in such environments, providing reaction rates and pathways that can be applied to interpret the astronomical observations. These collaborative efforts refine our understanding of molecular formation, gas cooling, and dust processes in space. Looking ahead, upcoming space telescopes equipped with advanced instrumentation promise to deepen our knowledge of the Boomerang Nebula and similar objects. Instruments capable of higher spectral resolution and sensitivity will allow astronomers to detect even more subtle molecular signatures and trace the motions of gas and dust with greater precision. This will help unravel the complexities of nebular evolution and the role of magnetic fields and binary interactions. The Boomerang Nebula represents one of the most fascinating and enigmatic phenomena in the universe. Its extreme cold, unique shape, and dynamic evolution combine to make it a cosmic wonder and a crucial piece in the puzzle of stellar and galactic evolution. Studying this nebula not only enhances our understanding of the physics of cold matter in space but also connects to profound questions about the origin of chemical complexity and the life cycle of stars that enrich the cosmos with the ingredients necessary for life. As we continue to explore the Boomerang Nebula, we are reminded that the universe is full of extremes and mysteries, where conditions that seem inhospitable by earthly standards nevertheless hold the keys to understanding the cosmic past, present, and future. The Boomerang Nebula, despite its otherworldly coldness, also holds clues about the life cycle of cosmic dust, an essential ingredient in the formation of stars, planets, and ultimately, life itself. Dust grains in space, composed of silicates, carbonaceous compounds, and ices, serve as the fundamental building blocks for planetary systems. These grains absorb and scatter starlight, influencing the thermal properties of their surrounding environment, and providing surfaces upon which chemical reactions can occur, creating complex molecules. The extreme cold of the Boomerang Nebula preserves these dust grains in a near-pristine state, allowing astronomers to study their characteristics in unparalleled detail. Dust formation begins in the outer layers of aging stars, such as the one at the heart of the Boomerang Nebula. As the star sheds its mass, the expelled gas cools enough to allow atoms and molecules to stick together, forming tiny solid particles. The nebula's unique conditions affect how these dust grains aggregate and evolve. The low temperature slows down the thermal motions that can disrupt these grains, enabling larger and more complex structures to form. Over time, these grains may become coated with icy mantles of frozen molecules, enhancing their chemical richness. Studying these dust grains provides insight into the processes that recycle stellar material into the interstellar medium, the vast space between stars filled with gas and dust. This material eventually condenses into new stars and planets, closing the cosmic cycle of matter. In this way, the Boomerang Nebula acts as a vital link between the death of one star and the birth of new celestial bodies. Beyond the physical and chemical processes, the Boomerang Nebula also invites philosophical reflections about the nature of the universe and our place within it. The extreme cold, so close to absolute zero, challenges our intuitive notions of temperature and life, pushing the boundaries of what is possible in nature. It invites us to ponder the diversity of environments that exist beyond Earth, and to imagine the myriad forms that matter and energy can take across the cosmos. The nebula's stark beauty, an ethereal, glowing boomerang-shaped cloud in the dark expanse of space, reminds us that the universe is as much a place of aesthetic wonder as it is a domain of physical laws. The interplay of light and shadow, heat and cold, matter and vacuum, produces a spectacle that has fascinated astronomers and enthusiasts alike since its discovery. Furthermore, the discovery and study of the Boomerang Nebula underscore the importance of human curiosity and technological advancement. It was only with the advent of powerful telescopes and sensitive detectors that such a cold and distant object could be identified and analyzed. This progress speaks to humanity's relentless pursuit of knowledge and the ever-expanding frontier of exploration. Scientists continue to develop new models and simulations to better understand the mechanisms at work in the Boomerang Nebula. These computational tools allow researchers to recreate the physical conditions and evolutionary history of the nebula, testing hypotheses about gas dynamics, cooling rates, and dust formation. Such models help predict the nebula's future, anticipating how it will evolve over thousands of years into a planetary nebula and eventually fade into the interstellar medium. Moreover, the Boomerang Nebula provides a benchmark for comparing other cold cosmic phenomena. Its uniquely low temperature challenges existing theories about cooling limits and sets new standards for observational astronomy. By studying similar objects, astronomers can develop a more comprehensive framework for understanding cold molecular clouds, star-forming regions, and the life cycle of stellar material. The nebula's existence also raises questions about the potential for extreme environments to host unexpected phenomena. Could there be exotic forms of chemistry, unknown molecular species, or even new states of matter stabilized at such low temperatures? These questions inspire ongoing research and exploration, driving the development of more sensitive instruments and innovative detection techniques. In the broader cosmic context, the Boomerang Nebula is a vivid illustration of the dynamic and ever-changing nature of the universe. Far from being static or uniform, space is filled with objects undergoing constant transformation, birth, evolution, decay, and renewal. Each object, from the hottest stars to the coldest nebulae, contributes to the intricate tapestry of cosmic history. As we gaze toward the Boomerang Nebula, we are reminded that the universe holds surprises in every direction. Its chilling cold, mysterious shape, and fleeting evolutionary stage offer not just scientific data but a narrative of cosmic change. Through continued observation and study, the Boomerang Nebula will remain a touchstone for understanding the extremes of nature and the processes that shape the galaxies. In summary, the Boomerang Nebula, with its record-setting temperature of just 1 Kelvin, stands as a remarkable natural laboratory for astrophysics and chemistry. Its unique conditions challenge and expand our knowledge of the universe, highlighting the complex interplay of forces that govern stellar death and cosmic recycling. As research progresses, this enigmatic nebula will continue to inspire wonder and deepen our appreciation for the diversity and richness of the cosmos. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.